They were never built to impress the modern world, yet thousands of years later they continue to do exactly that. Hidden among deserts, carved into cliffs, buried beneath forests, or standing alone against the horizon, these ancient monuments have outlived the civilizations that created them. Time has worn away their colours, broken their walls, and erased the names of many of their builders, but it has failed to erase the questions they left behind. Every weathered stone hints at forgotten knowledge. Every silent chamber suggests a purpose that has yet to be fully understood. The deeper we venture into these remarkable places, the more the ancient world begins to feel less like distant history, and more like a mystery that has been waiting patiently for us to uncover. Lahogue on the island of Jersey in the English Channel looks like nothing more than a grassy hill, yet hidden beneath it lies one of the oldest surviving stone monuments in Europe, constructed more than 6,000 years ago using nothing but stone, timber, rope, and tools made from polished stone and early bronze, long before the Iron Age transformed construction forever. Even after centuries of archaeological research, this monument continues to challenge modern understanding, not because of myths or legends, but because its engineering appears astonishingly advanced for a farming society that supposedly possessed only the simplest technology. The monument remained largely hidden beneath its massive earthen mound until systematic investigations during the 19th century revealed an exceptionally preserved Neolithic passage tomb. Excavations uncovered a long stone corridor leading into a central burial chamber together with pottery, stone tools, human remains, and ritual artifacts dating to roughly 4,000 to 3,500 BC. While these discoveries confirmed the monument's extraordinary age, they also introduced a far more difficult question. How could people who had neither iron tools nor wheeled vehicles design and build something displaying such remarkable precision and durability? That question becomes even more compelling the moment attention shifts from the mound itself to the narrow passage hidden inside. Stretching approximately 18.6 meters from entrance to chamber, the corridor is aligned so precisely that during the spring equinox, and under favorable conditions around the autumn equinox, the rising sun sends a beam of light directly through the entire passage until it reaches the innermost chamber. For only a brief period each year, sunlight travels almost 20 meters through an opening scarcely wider than a person before illuminating the sacred interior. Today, this phenomenon is easily verified with astronomical software, laser surveying equipment, and satellite positioning. Yet the builders possessed none of these technologies. They had no magnetic compass, no optical instruments, no written mathematical records, and no metal surveying equipment capable of measuring long distances with modern precision. Even a deviation of only a few degrees during construction would have prevented the sunlight from reaching its destination, suggesting that the alignment required years, perhaps generations, of careful observation of the rising sun across changing seasons. Archaeologists generally agree that repeated astronomical observations could explain the orientation. Yet exactly how Neolithic builders transferred those observations into an accurately constructed stone corridor remains uncertain. The monument demonstrates not only an understanding of celestial cycles, but also the practical ability to transform astronomical knowledge into permanent architecture with astonishing accuracy. As remarkable as the astronomical alignment may be, achieving it would have been impossible without solving an equally difficult engineering challenge. The burial chamber and passage are built from enormous granite slabs, several weighing between 15 and 25 metric tons. Jersey contains suitable stone, but transporting blocks of that size across uneven prehistoric terrain without iron tools, carts, cranes, or draft animals remains one of the site's greatest mysteries. Modern experimental archaeology has demonstrated that heavy stones can be moved using timber rollers, wooden sledges, ropes made from plant fibers, and large coordinated workforces. Yet none of these experiments perfectly reproduces the conditions at La Hougue B. Moving a 20-ton block is only the beginning. Builders then had to raise it into position with sufficient control to avoid catastrophic collapse, while ensuring that each supporting stone carried weight evenly across the entire structure. Every successful lift required precise coordination, because a single mistake could have destroyed months or years of work. Once the chamber had been assembled, another extraordinary project began. Instead of leaving the stone monument exposed, its builders covered the entire structure beneath an earthen mound measuring approximately 55 meters in length and rising around 12 meters above the surrounding landscape. Creating such a mound required moving tens of thousands of tons of soil, clay, and smaller stones entirely by human labor. No evidence suggests the use of wheeled transport, domesticated draft animals, or metal excavation equipment. Every basket of earth would have been dug, carried, and deposited by hand. The sheer volume of material implies careful planning, organized labor, and long-term cooperation among large communities. Yet archaeologists still debate how many workers participated and how many years the project required to complete. The engineering hidden beneath that mound has proven just as impressive as its construction. More than 6 millennia after completion, the stone passage remains largely intact, despite constant exposure to changing temperatures, moisture, ground movement, and thousands of seasonal freeze and thaw cycles. No mortar binds the stones together, no metal clamps reinforce the joints, and no artificial cement distributes the load. Stability depends entirely upon gravity, balance, and the careful selection of naturally shaped stones. Every supporting slab transfers weight into the surrounding structure with remarkable efficiency, preventing excessive stress from concentrating at any single point. Modern structural engineers recognize the effectiveness of compression-based stone architecture, yet the builders of La Hougue B achieved this long before written engineering principles existed anywhere in Europe. Closer examination of the passage reveals another subtle achievement that often receives less attention than the astronomical alignment. The corridor maintains an unusually consistent direction and width over nearly 19 meters, despite being constructed from irregular natural stones rather than carefully cut blocks. Unlike the precisely dressed limestone of later Egyptian monuments, the stones at La Hougue B preserve much of their natural form. Instead of reshaping every block into perfect geometry, the builders appear to have selected individual stones whose natural shapes complemented one another. This required an intuitive understanding of weight distribution, contact surfaces, and structural stability, developed entirely through experience rather than formal mathematics. Every decision increased the probability that the monument would survive for generations, and remarkably, it still stands thousands of years later. The monument also raises difficult questions about prehistoric surveying techniques. Constructing a corridor nearly 20 meters long while preserving both its orientation and structural alignment would have required reliable methods for establishing straight reference lines across uneven ground. Builders somehow maintained consistent dimensions while ensuring that the final chamber occupied exactly the position required by the solar alignment. Yet no measuring instruments have survived, and no written instructions describe the techniques used. Archaeologists have proposed the use of stretched cords, wooden stakes, sighting poles, and repeated observations of the horizon, but the precise construction process remains unknown. The absence of physical evidence means the most critical engineering knowledge may have disappeared completely with the people who built the monument. Even the foundation beneath the structure reflects a sophisticated understanding of construction. The immense stone slabs have experienced surprisingly little differential settlement considering the extraordinary loads they have supported for over 6,000 years. Before placing the stones, the builders appear to have selected stable ground, capable of supporting concentrated weight without significant movement. Whether this knowledge resulted from repeated practical experience or generations of accumulated observation remains impossible to determine. But the monument itself demonstrates that they understood the importance of preparing the ground before raising the structure above it. The greatest mystery of La Hougue is not how it was built, but why so much effort and precision were invested in a monument that was more than a simple tomb. While human remains confirm its funerary use, its precise solar alignment suggests it also served an astronomical purpose. The annual beam of sunlight reaching the inner chamber may have symbolized rebirth, marked seasonal cycles, or supported religious rituals. Whatever its meaning, the builders combined astronomy, engineering, and ritual into a structure far more complex than burial alone required. Set among the rolling hills of County Kilkenny, Ireland, Knockcrow Passage Tomb preserves one of prehistoric Europe's most sophisticated examples of stone engineering, where more than 5,000 years ago builders working with little beyond stone, timber, rope, and polished Bronze Age level technology created a monument whose astronomical precision still challenges modern explanation. The site remained largely concealed beneath a low mound until archaeological excavations directed by George Eogan during the 1990s revealed that what appeared to be an ordinary passage tomb was in fact one of the most technically unusual monuments ever discovered in Ireland. Radiocarbon dating places its construction around 3200 BC, making it broadly contemporary with Newgrange and Noath. Yet Knockcrow immediately stood apart, because excavators uncovered not one passage, but two entirely separate stone corridors extending from opposite sides of the mound. Every structural detail, from the placement of massive orthostats to the carved stones decorating the chambers, suggested that the builders had executed a carefully planned design rather than expanding the monument over time. For a society that had not yet entered the Iron Age and possessed neither steel tools nor written mathematics, the engineering ambition preserved beneath this quiet Irish hillside was extraordinary. What continues to fascinate archaeologists most is not simply that the monument aligns with the winter solstice, but that it appears to have been deliberately designed around two different solar events occurring on the very same day. One passage receives the first light of the winter solstice sunrise, while the other was oriented toward the setting sun at sunset, creating a dual astronomical system almost unknown among European passage tombs. This meant the builders were not merely identifying one direction on the horizon, they had to understand two completely different solar positions separated by nearly 12 hours, each influenced by different elevations of the surrounding landscape. The eastern and western horizons around Knockcrow are not mirror images of one another, meaning identical measurements would never have worked. Every angle had to be calculated independently, requiring observations extending across many years because the winter solstice can only be confirmed once each year. A single cloudy morning or evening would have delayed confirmation until the following winter, implying that astronomical knowledge had to be preserved across generations with remarkable consistency, despite the complete absence of written records. Even more remarkable is the evidence that the passages were intended to channel sunlight into the inner chambers using carefully constructed roof box openings similar in concept to the famous feature at Newgrange. These narrow apertures above the entrances are far more complex than they first appear. Their dimensions determine whether sunlight penetrates only a few meters or travels the full length of a corridor. The height of the opening, the thickness of the roofing slabs, the slope of the passage floor, and the exact orientation of the entrance all influence the final path of the sunlight. An error measured in only a few centimeters could shift the beam enough to miss the chamber entirely. Yet the surviving architecture demonstrates that prehistoric builders achieved a level of optical control usually associated with much later civilizations. No surviving evidence explains how these measurements were performed before precision instruments existed, making the construction process itself one of the monument's greatest unsolved technical mysteries. The challenge becomes even greater when considering the monument's overall geometry. The two passages do not intersect, despite extending deep into the mound from different directions. Such an arrangement required the builders to visualize the entire internal layout before construction began, because once dozens of multi-ton stones had been erected, correcting a mistake would have been nearly impossible. Every supporting orthostat had to occupy a predetermined position, while leaving sufficient space for both chambers to function independently. Modern excavations reveal no indication that major corrections were made during construction, suggesting that the design had been planned with surprising confidence from the outset. This level of spatial organization resembles architectural planning, rather than experimental building, raising questions about how prehistoric communities, without written drawings, transmitted complex construction plans between generations of craftsmen. The monument also illustrates the extraordinary logistical capabilities of Neolithic Ireland. Many of the structural stones weigh several tons and were transported from sources scattered across the surrounding landscape. None of the technologies later associated with monumental construction existed. There were no iron tools capable of quarrying efficiently, no wheeled vehicles for heavy transport, no draft animals pulling massive sledges, and no cranes to raise stones into position. Archaeologists have proposed combinations of timber rollers, wooden sledges, rope systems, earthen ramps, and coordinated human labor, yet no experimental reconstruction has demonstrated every stage required to reproduce the monument exactly as it survives today. The precision with which the orthostats were erected suggests careful control during lifting, but the mechanical methods capable of achieving that control remain uncertain. Adding another layer of complexity are the carved stones discovered throughout the monument. Spirals, concentric circles, zigzags, and lozenge motifs were engraved into selected slabs before they were incorporated into the structure. These decorations required thousands of repeated hammerstone impacts to shape hard stone surfaces, representing an enormous investment of labor for images that would often remain hidden within dark chambers. Their distribution appears deliberate rather than random, yet their purpose remains unknown. Some researchers argue that the carvings marked ritual pathways. Others propose symbolic representations of seasonal cycles or celestial motion, while still others believe they formed part of a ceremonial language now permanently lost. Despite decades of research, no interpretation has achieved universal acceptance because the symbols survive without any accompanying written explanation. Equally impressive is the structural durability of the monument itself. More than 5 millennia of Irish rainfall, seasonal temperature changes, and ground movement have failed to collapse significant portions of the surviving chambers. This stability was achieved without mortar, metal reinforcement, or any synthetic binding material. The builders instead relied entirely upon the weight, geometry, and balance of carefully selected stone blocks. Each roof slab distributes its load across upright supports, while the surrounding mound stabilizes the entire structure. Such engineering demonstrates an advanced practical understanding of compressive forces developed long before formal theories of architecture existed. The monument survives because its builders instinctively mastered principles that modern structural engineering would later describe mathematically. These achievements become even more remarkable when placed within the technological context of the period. Around 3200 BC, Ireland stood centuries before the introduction of iron metallurgy. Communities possessed polished stone tools alongside limited early metalworking traditions based on native copper and eventually bronze. Yet every stage of Knockro's construction depended overwhelmingly on materials that had been available since the Stone Age. There were no iron chisels capable of reshaping massive rock surfaces, no precision surveying instruments, no optical devices for measuring solar angles, and no written astronomical tables recording generations of observations. Nevertheless, the monument demonstrates an integration of architecture, astronomy, surveying, and structural engineering that rivals some of the best-known prehistoric sites in Europe. Traces of a monumental city built before the Iron Age lie beneath the coastal sands of Banduria, near Huacho, on Peru's central coast, where thousands of tons of stone were assembled into pyramids and ceremonial plazas by people who possessed neither iron tools, wheeled transport, nor draft animals. Radiocarbon dating places the earliest construction at around 3200 BC, making Banduria one of the oldest monumental centers in the Americas and a contemporary of the earliest phases of the Norte Chico civilization. Although local residents had long known of the mounds, Banduria attracted little scientific attention until the 1970s, when surveys recognized its archaeological significance. The site was later investigated in detail through excavations led by Peruvian archaeologist Alejandro Chu during the early 2000s, after looting exposed ancient deposits beneath the dunes. What emerged was not an isolated ceremonial mound, but a carefully planned settlement covering more than 50 hectares, containing platform pyramids, residential sectors, open plazas, and one of the earliest known sunken circular ceremonial courts in the New World. The deeper archaeologists excavated, the more difficult it became to explain how a society existing centuries before bronze metallurgy became widespread in the Andes could organize construction on such a scale, using little more than stone tools, wooden implements, woven fiber, and human labor. Every major platform required the movement of enormous quantities of rock across uneven terrain, yet no evidence has ever been found for wheeled vehicles, pack animals capable of hauling heavy loads, or sophisticated lifting machinery. Llamas had not yet become transport animals in this region, and the wheel, although known elsewhere as a toy in later Mesoamerican cultures, played no role in Andean construction. Every block, every basket of fill, and every beam appears to have been carried entirely by hand. Among the most remarkable engineering discoveries at Banduria is a construction technique known today as Shikra technology, one of the least appreciated yet most sophisticated structural innovations of the prehistoric world. Instead of filling pyramid foundations with loose rubble, builders wove large bags from reeds and vegetable fibers, filled each bag with carefully selected stones, then stacked thousands of these stone-filled sacks deep inside the platforms before covering them with additional masonry and earth. At first glance, the method appears surprisingly simple, but modern engineering analysis suggests it solved several structural problems simultaneously. The flexible woven containers prevented individual stones from shifting freely, distributed loads more evenly throughout the foundation, reduced differential settlement, and created internal layers capable of absorbing part of the energy generated during earthquakes. In effect, the builders produced a massive composite foundation that behaved very differently from ordinary piles of rock. This is particularly striking because Peru sits along one of the most seismically active regions on Earth, where the Nazca Plate continuously subducts beneath the South American plate, generating frequent earthquakes over thousands of years. Yet significant portions of Banduria's monumental architecture have survived nearly 5 millennia despite repeated seismic events. Archaeologists do not argue that the builders possessed a scientific understanding of plate tectonics, but they clearly developed construction methods that dramatically improved structural stability under local conditions. Whether this knowledge emerged through centuries of observation and experimentation, or through systematic engineering traditions passed between generations, remains unknown, because no written records survive to explain how such techniques evolved. The mystery becomes even greater when considering the sheer scale of the work involved. A single monumental platform required tens of thousands of stone-filled shikra bags, each individually woven, transported, filled, positioned, and incorporated into carefully prepared layers. Producing enough woven fiber alone demanded an enormous investment of labor before construction even began. Every bag had to maintain sufficient strength while buried under the weight of thousands of additional tons of material, meaning the weaving techniques themselves had to achieve remarkable consistency. Very few prehistoric societies anywhere in the world are known to have relied on such a large-scale integration of textile technology directly into monumental architecture, making Banduria's foundations unlike almost anything else from the 4th millennium BC. The architecture above these foundations raises equally intriguing questions. Several pyramidal platforms follow consistent orientations, while the central ceremonial district revolves around a carefully excavated, sunken circular plaza, a design that later became one of the defining characteristics of early Andean ceremonial centers. Constructing a nearly symmetrical circular court several meters below ground level without modern surveying equipment required surprisingly accurate geometric planning. There is no evidence for metal measuring instruments, graduated rulers, or written architectural plans, yet the builders produced balanced layouts whose proportions suggest deliberate design rather than gradual accumulation. Archaeologists generally believe simple cords, wooden stakes, and repeated measurements were sufficient, but the precise procedures remain entirely hypothetical because none of the construction tools have survived. The planning visible across the settlement indicates that Banduria was not built randomly over generations. Residential sectors, ceremonial architecture, open spaces, and circulation routes form an integrated layout that appears to have followed an overall plan from an early stage of development. Such organization implies centralized decision-making capable of coordinating hundreds or perhaps thousands of workers over extended periods. Yet, unlike many later civilizations that left royal inscriptions, palaces, or military monuments, Banduria preserves almost no direct evidence identifying the individuals responsible for directing these immense public works. The administrative system behind one of South America's oldest monumental centers therefore remains largely invisible. Excavations have also revealed that the community depended heavily on marine resources despite its monumental inland architecture. Large quantities of fish bones, shellfish remains, fishing equipment, and botanical evidence indicate an economy combining intensive coastal exploitation with agricultural products obtained through exchange networks reaching inland valleys. Cotton appears to have played a particularly important role because it supplied fiber for fishing nets, ropes, and most importantly, the woven shikra bags that became essential to large-scale construction. This close relationship between maritime resources and monumental architecture challenges older assumptions that only agricultural surpluses could support early civilizations. Instead, Banduria demonstrates that abundant marine productivity may have generated enough economic surplus to finance ambitious public building projects long before complex states fully emerged. Another unresolved question concerns the spread of engineering knowledge itself. Bandurria shares striking architectural similarities with nearby ceremonial centers such as Carroll, Aspero, and several other settlements belonging to the broader Norte Chico cultural sphere. Sunken circular plazas, platform pyramids, and shikra foundations appear repeatedly across multiple sites, separated by considerable distances. The similarities are too systematic to dismiss as coincidence, yet no writing system existed to preserve architectural manuals, construction formulas, or technical instructions. Knowledge must therefore have been transmitted entirely through oral tradition and practical apprenticeship. How such sophisticated engineering standards remained consistent across generations without written documentation remains one of the least understood aspects of early Andean civilization. Traces of an engineering tradition that existed before iron changed human history still crown the Brickleave Mountains of County Sligo, Western Ireland, where the Carrowkeel Passage tombs have remained standing for more than 5,000 years, despite being built using nothing more than stone, timber, rope, and Bronze Age, or even late Neolithic technology. Long before cranes, mortar, steel tools, or written engineering manuals, people carried enormous slabs onto windswept mountain summits and assembled chambers whose roofs continue to resist gravity today almost exactly as they did around 3600–3400 BC. Although local people had always known of the cairns scattered across the mountains, the complex entered archaeological study after systematic investigations by George Coffey and Hugh O'Neill Henkin during the early 20th century, followed by extensive modern surveys using aerial photography, GPS mapping, LiDAR, and radiocarbon dating. These studies revealed that Carrowkeel is not a single monument, but a ceremonial landscape containing roughly 30 passage tombs spread across several mountain peaks, covering nearly 10 square kilometers. Excavations uncovered cremated human remains, polished stone balls, bone pins, antler tools, pottery, quartz fragments, and carefully constructed burial chambers, confirming that this was one of Ireland's most important ceremonial centers during the Neolithic period. Yet the discoveries answered only part of the story because the greatest mystery begins with the mountain itself. Unlike many prehistoric settlements built in fertile valleys, Carrowkeel occupies exposed limestone summits rising between approximately 340 and 380 meters above sea level. Every large capstone, orthostat, and wallstone had to be transported uphill across rugged terrain long before wheeled transport became common in northwestern Europe. Several structural slabs weigh multiple tons, while the cairns themselves contain thousands of smaller stones arranged with remarkable precision. Archaeologists have proposed timber sledges, wooden rollers, rope systems, seasonal movement over frozen ground, and large coordinated workforces. Yet none of these explanations has been demonstrated experimentally at the scale required to reproduce the entire construction process. No prehistoric drawings, inscriptions, or surviving traditions explain how these communities repeatedly completed such projects on remote mountain ridges using only simple tools. That question becomes even more remarkable after stepping inside one of the chambers, because the engineering is hidden above the visitor's head. The most astonishing feature of several Carrowkeel tombs is the corbelled stone roof, a structural solution achieved without mortar, metal reinforcement, or the true arch that would later become famous in Roman engineering. Massive stone courses were stacked one above another, with each layer projecting slightly inward, until the opening narrowed enough to be sealed by a final capstone. Every individual slab supports the next through carefully balanced compression, allowing gravity itself to lock the structure together. More than 5,000 years of Atlantic storms, winter frost, heavy rainfall, seasonal temperature changes, and constant wind have failed to collapse many of these chambers. Modern structural engineers recognize that such roofs depend upon extremely accurate control of weight distribution, center of mass, stone geometry, and friction between each contact surface. If only a few stones had been placed at incorrect angles or with uneven load paths, the inward pressure would eventually have pushed the walls outward, causing progressive failure. Instead, many roofs remain remarkably stable after over 50 centuries, making them among the oldest surviving examples of sophisticated dry stone engineering anywhere in Europe. The builders left no mathematical formulas, no measurements carved into stone, and no written explanation of their design principles. Yet the finished structures demonstrate an understanding of structural behavior that continues to surprise engineers today. The precision extends beyond the roof itself, because the chambers are integrated into the surrounding cairns with equally deliberate planning. Rather than piling rocks randomly over burial spaces, the builders created layered systems in which retaining walls, passage stones, chamber walls, and outer cairn material all work together as a single structural unit. The weight of thousands of smaller stones pressing inward stabilizes the larger orthostats while simultaneously protecting the chamber from weathering. This relationship between architecture and fill material resembles principles still employed in modern retaining structures, yet it was achieved entirely through empirical knowledge accumulated thousands of years before formal engineering existed. As researchers continued examining the complex, another pattern gradually emerged that shifted attention from structural engineering toward precision planning. Several tombs, particularly Cairn G, appear deliberately aligned with the setting sun around the summer solstice. During a narrow seasonal window, sunlight travels through the long entrance passage before reaching the inner chamber for only a brief period. Producing this effect required more than simply pointing an entrance toward the western horizon. The builders had to account for the local skyline formed by surrounding mountains, the annual movement of the sun, the length and width of the passage, and the exact elevation of the chamber floor relative to the entrance. A deviation of only a few degrees during construction would have prevented the illumination from occurring. Achieving such accuracy without compasses, optical instruments, or written astronomy suggests generations of careful observation passed from one community to the next. The mountain itself also appears to have been selected with unusual intention. Standing among the cairns, visitors can observe vast panoramas stretching across County Sligo toward Lough Arrow, Knocknarea, Ben Bulben, and the Ox Mountains. Geographic information system analyses indicate that many of the tombs occupy visually interconnected positions, creating sightlines between monuments and prominent natural landmarks. Rather than isolated graves scattered randomly across a landscape, Carrow Keel increasingly resembles a carefully organized ceremonial network in which topography, visibility, architecture, and celestial observation were designed to function together. Whether this planning occurred during a single construction program or developed gradually over centuries remains one of the site's unresolved questions. The selection of building materials introduces another layer of technical sophistication. Although limestone dominates the mountains, builders did not simply use whatever stone lay nearest. Different rock types appear in different architectural roles, suggesting deliberate choices based upon strength, shape, durability, or workability. Larger structural slabs with naturally flat surfaces were often reserved for chambers and passages where stable load-bearing performance was essential, while other stones filled retaining walls and cairns. Such decisions imply practical knowledge of material properties acquired entirely through experience rather than scientific testing. Excavations have also revealed engraved stones bearing spirals, arcs, cut marks, and geometric motifs, though the artwork at Carrowkeel is less abundant than at Newgrange. The limited distribution of these carvings is perhaps more intriguing than their quantity, because they appear only at carefully selected locations within particular chambers. Whether they marked ritual spaces, encoded astronomical knowledge, represented symbolic beliefs, or served purposes now completely forgotten remains unknown. Their placement reinforces the impression that almost every component of these monuments was intentional rather than decorative. A stone monument unlike almost anything else from the prehistoric Americas stands in Peru's Casma Valley. Cerro Sechin, built centuries before iron tools existed, surrounds its walls with hundreds of massive carved stone slabs that appear to depict dismembered human bodies in astonishing anatomical detail, raising a question that archaeologists still cannot fully answer. How did a society armed with little more than stone hammers and limited bronze technology create one of the ancient world's most disturbing masterpieces? Located about 15 kilometers from the Pacific coast in northern Peru, Cerro Sechin forms part of the larger Casma Sechin archaeological complex, one of the earliest centers of civilization in the Andes. The monument was first identified by local residents long before scientific excavation began, but its importance only became clear in 1937, when the Peruvian archaeologist Julio C. Tello carried out systematic investigations and uncovered the extraordinary carved perimeter walls hidden beneath centuries of accumulated soil and collapsed construction. Later excavations by Federico Engel and other researchers revealed that the visible temple represents only one phase of a much longer architectural sequence extending back to the late Archaic and Initial period, while radiocarbon dating places the principal stone complex around 1800 to 1500 BC, making it older than many famous monuments traditionally associated with advanced stone carving. Even after decades of excavation, however, the greatest mystery is not when Cerro Sechin was built, but how such technical precision emerged before the widespread use of iron metallurgy anywhere in the Andes. The first puzzle begins with the stone itself. More than 300 carved monolithic slabs form the exterior walls of the ceremonial structure, many standing over 2 meters tall and weighing several tons. Most were shaped from locally available granite and other hard igneous rocks, with hardness values approaching 6 or 7 on the Mohs scale. Archaeological excavations have recovered abundant hammerstones made from even harder rocks, such as quartzite and dolerite, along with evidence that abrasive sand rich in quartz was likely used to grind surfaces smooth. Experimental archaeology demonstrates that such methods are physically possible, yet reproducing even a single relief requires enormous amounts of labor, while Cerro Sechin contains hundreds of carvings executed with remarkable consistency. Fine grooves, deeply recessed contours, clean edges, and carefully proportioned figures suggest that generations of craftsmen followed an established technical system, although no written plans, measuring guides, or workshops have ever been discovered to explain how this level of standardization was maintained. The engineering challenge becomes even greater when considering transportation. Although suitable stone exists within the Casma Valley, many of the blocks still had to be quarried, shaped, moved, and positioned with considerable precision. There is no evidence that the builders possessed wheeled transport for construction, nor were horses, oxen, or other large draft animals available in prehistoric Peru. Every monolith, therefore, had to be moved through human labor alone. Archaeologists propose combinations of wooden rollers, fiber ropes, earthen ramps and coordinated work crews, yet almost all organic materials that might confirm these techniques disappeared thousands of years ago in the coastal environment. Unlike Egyptian pyramids, where quarry marks, unfinished ramps and transport traces survive in several locations, Cerro Sechin preserves remarkably little direct evidence of the engineering process itself, leaving modern researchers to reconstruct the entire logistical system largely through experimentation rather than archaeological proof. As the technical questions deepen, the carved imagery introduces an even greater mystery. The walls are unlike ordinary decorative reliefs found elsewhere in the ancient world. Instead of celebrating rulers or recording victories with orderly processions, the stone slabs display severed heads, detached limbs, exposed ribs, spinal columns, intestines, eyeballs, and internal organs carved with startling realism. Some figures stand upright holding ceremonial knives or clubs, while others appear to be lifeless victims whose bodies have been systematically disassembled. The anatomical precision has fascinated researchers for decades because many organs are positioned correctly relative to the human skeleton rather than being arranged symbolically. Muscles, vertebrae, and tendons are represented with a level of observation unexpected for a civilization without written anatomical knowledge. This has led to competing interpretations that remain unresolved. One theory argues the reliefs commemorate military victory over defeated enemies, yet archaeological evidence for warfare on such a massive scale during this period remains surprisingly limited. Another suggests they depict ritual human sacrifice connected with agricultural fertility or ancestor worship. Although excavations have failed to uncover large cemeteries or sacrificial deposits matching the extraordinary number of carved victims. A third interpretation proposes that the artists intentionally documented the transformation of the human body after death as part of religious beliefs concerning renewal and cosmic order. None of these explanations accounts for every detail, and no accompanying inscriptions survive to reveal the original meaning intended by the builders. The possibility that these reliefs preserve unusually advanced anatomical knowledge remains especially controversial. Several scholars have noted that certain carved organs appear recognizable as intestines, spinal columns, vertebrae, and detached musculature rather than abstract symbols. Such accuracy could have resulted simply from repeated observation during ritual sacrifice, warfare, or funerary preparation, rather than formal medical investigation, yet the consistency of the carvings implies that artists worked according to established visual conventions rooted in direct experience. Whether this represents practical anatomical understanding or highly stylized religious symbolism continues to divide specialists, making Cerro Sechin one of the earliest archaeological sites where artistic realism intersects with unresolved questions about prehistoric scientific observation. Beneath the carved walls, another layer of technological sophistication emerges. Excavations reveal that Cerro Sechin was not constructed as a single project, but expanded through multiple architectural phases. Earlier buildings were intentionally buried beneath thick layers of stone and fill before entirely new ceremonial structures rose above them. Instead of demolishing previous temples, the builders sealed them almost intact, preserving earlier architecture inside artificial platforms that gradually increased the monument's size. This method required enormous quantities of labor and construction material, suggesting long-term planning extending across generations. Similar practices later appeared at other ceremonial centers, including Sechin Bajo and several early Andean temple complexes, indicating that the concept formed part of a broader engineering tradition rather than an isolated experiment. Why these buildings were deliberately entombed instead of reused remains unknown, but the repeated rebuilding demonstrates remarkable organizational ability long before centralized empires emerged in Peru. The layout itself reflects careful planning, despite the complete absence of surviving written mathematics. The ceremonial core follows a strongly ordered arrangement of plazas, stairways, corridors, and enclosed spaces organized around a central axis. Individual carved slabs fit together with surprising regularity despite natural variations in stone size and shape. Maintaining alignment across hundreds of heavy blocks would have required reliable methods of measurement, leveling, and orientation, yet archaeologists have recovered no rulers, marked measuring rods, or standardized units. The builders almost certainly relied on cords, stakes, repeated geometric procedures, and accumulated practical knowledge, but the exact surveying techniques remain invisible within the archaeological record. Even the monument's original appearance may have differed dramatically from what visitors see today. Microscopic pigment analyses have identified traces of mineral-based red, yellow, black, and white coloration adhering to portions of the reliefs, suggesting the famous stone walls were once vividly painted rather than left bare. Under intense Andean sunlight, these brightly colored anatomical scenes would have been visually overwhelming, transforming the temple into a ceremonial display far more dramatic than the weathered grey surfaces preserved today. Exactly how the pigments were prepared, applied and maintained across exposed stone remains uncertain because only tiny remnants survived thousands of years of erosion. Kotosh Temple of the Crossed Hands, high in Peru's Huallaga Valley, preserves a 4,000-year-old architectural secret built entirely with stone, clay, and Bronze Age technology, yet parts of its walls have outlasted structures erected thousands of years later. The temple stands near modern Huánuco, in the central Andes of Peru, about 1,900 meters above sea level, where excavations led by the Japanese archaeological mission under Seiichi Izumi in the late 1950s and early 1960s revealed one of South America's oldest ceremonial centers. Beneath layers of later construction, archaeologists uncovered an exceptionally well-preserved ritual chamber containing the famous crossed hands clay reliefs still attached to the original walls. Radiocarbon dating places the Temple of the Crossed Hands between roughly 2500 and 1800 BC, centuries before the rise of Chavin culture and well before iron metallurgy reached the Andes. The builders possessed neither iron tools nor wheeled transport, relying instead on stone implements, wooden tools, woven fiber ropes, and the limited bronze technology that would only appear in later Andean metallurgy, making the precision and durability of the structure all the more remarkable. What immediately distinguishes Kotosh from countless other prehistoric temples is that its builders never demolished the sanctuary when rebuilding. Instead, every generation deliberately buried the previous temple intact beneath carefully placed layers of soil, stone, and fill before constructing a new ceremonial building directly above it. This sequence repeated multiple times across many centuries, producing an archaeological record resembling nested architectural time capsules. The older walls remained standing, ritual features were left untouched, and sacred spaces disappeared beneath tons of carefully compacted material rather than being dismantled for reusable stone. Archaeologists still debate why such an enormous investment of labor was devoted to preserving buildings that would never again be seen. If practical construction had been the priority, dismantling the earlier structures would have been vastly more efficient, yet preservation clearly mattered more than convenience. That unusual rebuilding tradition naturally leads to another puzzle. Because every temple became sealed inside later construction, many internal surfaces survived in remarkably stable condition. The famous crossed hands, modeled directly from clay onto the interior wall, remained protected for nearly 4 millennia. Similar clay decorations exposed to weather elsewhere in the Andes usually eroded away long ago. Yet these reliefs still retain their original form with extraordinary clarity. Researchers believe the repeated burial process unintentionally created a controlled microenvironment that minimized moisture fluctuations, temperature extremes, biological activity, and erosion, although the complete combination of environmental factors responsible for such preservation remains incompletely understood. Even more remarkable than the sculptures are the walls supporting them. Kotosh was not built from massive granite blocks like later Inca monuments, nor from fired brick like many ancient civilizations in the Near East. Its builders relied primarily on locally available stone foundations, clay plaster, compacted earth, and carefully selected soils. By modern expectations, these materials should have deteriorated rapidly in an active mountain environment subject to seasonal rainfall, fluctuating humidity, earthquakes, and thousands of years of natural weathering. Instead, significant sections of the ceremonial chambers remained structurally intact until excavation. Some of these earthen walls survived longer than medieval masonry, colonial adobe settlements, and numerous later constructions across the Andes. This unexpected longevity remains one of the site's greatest engineering mysteries, because archaeologists still cannot fully explain why these particular walls endured, while many younger earthen buildings disappeared almost completely. Detailed analysis suggests that the answer extends far beyond simply using good clay. The walls were constructed in successive compacted layers rather than as uniform masses, with different sediment textures apparently selected for different structural purposes. Clay composition varies noticeably between construction phases, implying that builders intentionally chose specific local materials instead of using whatever soil happened to be nearby. Microscopic studies have identified carefully sorted mineral grains and evidence of repeated surface finishing, while traces of organic fibers may have strengthened portions of the plaster. Yet despite decades of laboratory examination, no universally accepted reconstruction of the complete building recipe exists. Researchers continue debating whether plant fibers, ash, fine sand, weathered volcanic minerals, or other natural additives contributed to the remarkable mechanical stability of the finished walls. Whatever the exact formula, it consistently produced structures capable of surviving nearly 4,000 years despite being composed largely of earth. The engineering becomes even more intriguing when viewed alongside the temple's internal layout. Each ceremonial chamber centers on a carefully constructed hearth, surrounded by raised platforms and symmetrically arranged wall niches. Excavations recovered thick accumulations of charcoal and ash, confirming that ritual fires burned repeatedly over long periods. Yet smoke staining inside several chambers appears less severe than expected considering centuries of continuous burning in enclosed spaces. This observation has led some researchers to suggest that subtle air circulation may have been incorporated into the architecture through openings or roof designs that no longer survive. Because the upper portions of the buildings have almost entirely disappeared, reconstructing the original ventilation system remains extremely difficult, leaving open the possibility that these early builders possessed a practical understanding of airflow that cannot now be observed directly. The remarkable geometric consistency of the rooms adds another layer to the mystery. Opposing walls remain closely aligned, niches are positioned with striking symmetry, and ceremonial features consistently occupy central axes, despite the complete absence of iron measuring instruments or advanced surveying equipment. Builders working with stone tools and simple measuring cords nevertheless achieved layouts that remained stable through repeated rebuilding episodes over centuries. Similar precision appears at several other late pre-ceramic ceremonial centers in Peru, suggesting that standardized construction knowledge circulated widely long before the emergence of large states or written records in the Andes. Exactly how this technical knowledge was transmitted between generations without written architectural plans remains unknown. earthquakes present another unresolved question. Peru lies along one of the world's most active subduction zones, where destructive seismic activity has repeatedly reshaped the landscape for thousands of years. Although Kotosh undoubtedly suffered damage during its long history, portions of the buried ceremonial architecture remained standing through countless seismic events. Some engineers have proposed that layered foundations composed of compacted earth and small stones distributed stress more effectively than rigid monolithic bases, while others argue that the flexibility of clay construction itself may have absorbed ground movement better than harder materials. These ideas remain plausible rather than proven, because too little of the original superstructure survives for comprehensive structural modeling. Perhaps the greatest technological mystery lies not within what archaeologists discovered, but within what they failed to find. Excavations produced ritual artifacts, stone tools, grinding implements, charcoal, botanical remains, animal bones, and ceremonial objects. Yet relatively few construction tools capable of explaining every stage of the building process have been recovered. There is no surviving instruction manual, no workshop preserving specialized equipment, and no written record describing how raw earth became architecture capable of resisting centuries of environmental stress. The practical knowledge clearly existed, but nearly every detail of that engineering tradition disappeared with the people who developed it. North Yorkshire, England. Along a remote stretch of cliffs facing the North Sea, an industry emerged in the 17th century that produced one of the most valuable chemical substances in Europe. The mystery is not what they made. The mystery is how they knew where to find it. The remains of Yorkshire's alluvium works were documented throughout the 18th and 19th centuries, but systematic archaeological investigation accelerated during the 20th century. Researchers uncovered massive burning platforms, extraction pits, reservoirs, stone tanks, transport routes, and industrial waste deposits stretching for kilometres along the coastline. These ruins revealed that North Yorkshire once hosted one of the largest chemical industries in Europe before the Industrial Revolution. This is the greatest mystery of all. Alum, chemically known as hydrated potassium aluminum sulfate, was one of the most important industrial chemicals in pre-industrial Europe. It was essential for fixing dyes in textiles, preserving leather, manufacturing medicines, and supporting numerous crafts. During the 16th century, Europe depended heavily on alum imported from Italy, particularly from the papal-controlled deposits at Tolfa. Then something remarkable happened. Around the late 16th century, English entrepreneurs discovered that the dark Jurassic shale exposed along the cliffs of North Yorkshire contained the ingredients necessary to manufacture alum. The question that continues to puzzle historians is simple. How did they know? The Yorkshire coast contains millions of tons of black shale, and most of it appears unremarkable. To the untrained eye, it looks no different from countless other rock formations across Britain. Yet hidden within specific layers were sulfur-bearing minerals, particularly pyrite, capable of producing the chemical reactions required for alum production. No geological surveys existed, no chemical laboratories existed, and no modern mineral analysis existed, yet someone identified the correct rock. One theory suggests that English agents secretly obtained industrial knowledge from Italy. Historical records indicate that experienced alum workers from the continent may have been recruited to England despite efforts by foreign powers to protect their monopoly. Another theory argues that local observers noticed similarities between Yorkshire shale and alum-bearing rocks described elsewhere in Europe. Neither explanation fully solves the mystery. Finding a useful rock formation is one challenge, but identifying thousands of hectares of productive shale among vast coastal exposures is another. Modern mining companies employ geologists, geochemical testing, satellite imagery, and drilling programs. The first Yorkshire alum producers had none of these tools. The situation is comparable to finding a hidden copper deposit without geology, locating petroleum without seismic surveys, or identifying uranium without radiation detectors. Somehow, knowledge existed before the science needed to explain it. Even today, historians cannot reconstruct the exact process through which Yorkshire's alum deposits were first recognised. After extraction, the shale underwent a process that appears astonishing even by modern standards. Workers piled enormous quantities of rock into vast mounds, sometimes reaching several meters in height and extending across large areas. These piles were then ignited and allowed to burn continuously, not for days, not for weeks, but for months. Historical accounts suggest that some burning cycles lasted between 6 and 12 months before completion. The objective was to oxidize pyrite contained within the shale. During combustion, sulfur compounds reacted with oxygen, generating sulfuric acid and initiating complex chemical transformations necessary for alum production. The mystery lies in control. Modern industrial roasting operations rely upon thermometers, airflow monitoring, automated systems, and chemical analysis. Yorkshire workers possessed none of these technologies. If temperatures became too low, reactions would remain incomplete. If temperatures became too high, valuable compounds could be destroyed. Yet generation after generation managed to achieve the desired result. Archaeological evidence indicates that workers carefully managed ventilation pathways within the burning heaps. However, researchers still debate exactly how temperatures were monitored and controlled. Much of this expertise appears to have been transmitted orally and vanished when the industry declined. Perhaps the most fascinating aspect of the Yorkshire alum industry is that it operated successfully before the scientific revolution fully explained the processes involved. The first commercial alum works appeared decades before modern chemistry emerged as a formal scientific discipline. Workers understood procedures, but they did not necessarily understand molecules. They understood outcomes, but they did not understand atomic structure. They knew which materials to combine, how long to burn the shale, how to process solutions, and when crystallization was complete. But concepts such as oxidation reactions, molecular bonds, and chemical equilibrium remained centuries away. This situation resembles other technological mysteries throughout history. Roman engineers produced durable concrete without understanding modern materials science. Medieval blacksmiths manufactured Damascus steel without knowledge of crystallography. The builders of the Antikythera mechanism created an analog computer nearly 2,000 years before modern mechanical engineering emerged. Yorkshire alum workers belong to the same tradition of practical expertise, exceeding contemporary scientific theory. Once roasting was complete, the shale had to be processed using large quantities of water. The solution sounds simple, but the reality was not. Many alum works occupied steep coastal locations where terrain presented major engineering challenges. Water had to be collected, directed, stored, and distributed across multiple processing stages. Archaeologists have identified extensive systems including reservoirs, channels, settling tanks, leaching pits, and evaporation facilities. Gravity performed much of the work. Instead of relying upon pumps, engineers designed layouts that allowed liquids to move naturally through successive stages of production. This required an understanding of gradients, flow rates, storage capacity, and hydraulic behavior. Some industrial complexes covered several hectares and processed thousands of tons of material annually. Their hydraulic sophistication rivals certain mining operations of later centuries. Yet no detailed engineering manuals survive. The physical structures remain, but the design logic behind them often does not. One of the most unusual aspects of alum production involved an ingredient found in virtually every community: human urine. Historical records indicate that urine was collected and incorporated into stages of the manufacturing process. To modern observers, this seems bizarre, but chemically it makes sense. Urine contains ammonia-producing compounds that influence reactions within processing solutions. The remarkable detail is that workers recognized its usefulness centuries before modern biochemistry explained why it worked. Communities sometimes participated in collection programs supplying industrial facilities with raw materials. This created a chemical supply chain based on empirical observation rather than scientific understanding. People knew the method worked, but few could explain the underlying chemistry. Yorkshire's alum industry operated on a vast scale. Millions of tons of shale were quarried, transported, burned, washed, and refined long before modern machinery existed. Workers extracted rock from coastal cliffs, moved it across difficult terrain, maintained burning heaps and hydraulic systems, and processed chemical solutions. The ruins reveal the industry's immense scale, but many details of how it functioned remain unknown. How do you think the first producers discovered that Yorkshire shale could be transformed into alum without modern science? Monte Alegre State Park lies on the northern bank of the Amazon River in Para, Brazil. Hidden among isolated sandstone hills rising above the rainforest are traces of a civilization whose technological abilities continue to challenge modern explanations. The mystery first emerged when archaeologists began systematic investigations of caves and rock shelters in the region during the late 20th century. Excavations at Pedra Pintada and neighbouring sites revealed stone tools, ancient hearths, food remains and rock paintings associated with human occupation dating back more than 11,000 years. These discoveries shocked researchers because they contradicted long-standing theories that the Amazon was settled relatively late and lacked complex prehistoric cultures. Instead, Monte Alegre suggested that sophisticated communities were already thriving near the end of the Ice Age. What makes Monte Alegre remarkable is not the presence of ancient people alone. The true mystery lies in the advanced knowledge systems hidden behind the surviving evidence. The site presents a combination of astronomical observation, landscape engineering, artistic technology, environmental adaptation, and information preservation that remains only partially understood. Among the most intriguing puzzles is the apparent relationship between the rock formations and the sky. Several archaeological investigations have identified locations where sunlight passes through natural openings or illuminates specific sections of rock surfaces during particular times of the year. Some researchers have suggested that certain markings may correspond to seasonal solar events such as solstices. If this interpretation is correct, the implications are extraordinary. Measuring the annual movement of the sun requires repeated observations over many years. Even a small error can shift predicted alignments by significant distances. Ancient observers would have needed a deep understanding of horizon markers, seasonal cycles, and solar motion. Similar astronomical discussions surround famous sites such as Stonehenge in England and Chanquillo in Peru, both regarded as among the earliest known solar observation complexes. Yet Monte Alegre predates many of these traditions, raising difficult questions about how much astronomical knowledge existed in prehistoric Amazonia. The challenge becomes even greater when the geography of the region is considered. The sandstone hills surrounding Monte Alegre provide commanding views across vast portions of the Amazon basin. From elevated points, ancient inhabitants could observe river systems, migration routes, seasonal flooding patterns, and celestial events. Some archaeologists argue that selecting these locations required a sophisticated understanding of landscape surveying. Without maps, compasses, or modern instruments, people consistently chose positions that maximize visibility and strategic advantage. Such decisions suggest a level of environmental planning far beyond simple survival. The rock art itself presents another engineering mystery. Hundreds of paintings are distributed across cliffs, shelters, and cave walls. Many are located in positions that remain difficult to access even today. Some paintings appear on steep rock faces several meters above the ground. Creating them would likely have required temporary platforms, climbing systems, scaffolding, or carefully designed support structures. Yet the humid tropical environment rapidly destroys organic materials, leaving little direct evidence behind. Researchers therefore face an unusual problem. The artwork survives, but the technology used to create it has vanished. The most fascinating puzzle involves the pigments themselves. Many of the paintings retain visible coloration despite exposure to thousands of years of environmental stress. In an ecosystem characterized by intense rainfall, extreme humidity, biological activity, and fluctuating temperatures, long-term pigment preservation should be exceptionally difficult. Nevertheless, red paintings remain visible across multiple sites throughout Monte Alegre. Scientific analyses indicate that iron oxide was likely a primary component of the red pigment. Iron oxide is common in prehistoric art around the world and was also used at sites such as Lascaux in France and Altamira in Spain. However, mineral colorants alone do not automatically survive for millennia. They require adhesion to rock surfaces and resistance to chemical degradation. This is where the mystery begins. Researchers suspect that prehistoric artists may have mixed iron-rich minerals with organic binding agents derived from plants, tree resins, oils, animal fats, or other natural compounds. Such mixtures could have increased durability and resistance to weathering. The problem is that most organic ingredients decompose over time, making precise reconstruction extremely difficult. Despite advances in microscopy, spectroscopy, and chemical analysis, scientists still cannot fully reproduce the exact formulation that allowed some Monte Alegre pigments to remain visible for more than 10,000 years. The scale of this achievement becomes clearer through comparison. Many historical paints used in medieval structures survive only a few centuries before requiring restoration. Modern outdoor pigments frequently deteriorate within decades when exposed to harsh environmental conditions. Yet some Monte Alegre paintings have persisted since the closing stages of the Pleistocene. The durability suggests an unexpectedly sophisticated understanding of material properties, whether developed intentionally through experimentation or accumulated through generations of practical knowledge. Equally puzzling is the consistency of pigment performance across different locations. If the artists were using locally gathered minerals, they must have possessed methods for identifying suitable deposits, processing raw materials, controlling particle size, and preparing mixtures capable of bonding effectively to stone surfaces. These are not random actions. They represent a chain of technical decisions comparable in principle to early chemical engineering. The environmental challenges faced by Monte Alegre's inhabitants create another layer of mystery. Around 11,000 years ago, the Amazon basin was undergoing significant climatic transitions associated with the end of the last ice age. Ecosystems were changing, river systems were shifting, and vegetation patterns were evolving. Maintaining stable communities under such conditions would have required detailed ecological knowledge. Archaeological evidence indicates that inhabitants exploited diverse food sources, including fish, fruits, nuts, and terrestrial animals. Managing these resources across changing environments suggests an advanced understanding of seasonal cycles and landscape productivity. This adaptability challenges traditional assumptions about prehistoric Amazonian populations. For decades, scholars often portrayed early Amazon communities as small, isolated groups limited by environmental constraints. Monte Alegre increasingly points toward a different picture. The evidence suggests people capable of organizing labor, transmitting knowledge across generations, and mastering complex environmental systems. Their achievements were not expressed through monumental stone pyramids or massive cities. Instead, they were embedded within observation material science, ecological management, and symbolic communication. The geometric motifs found among the paintings deepen the mystery further. Alongside depictions of humans and animals are circles, grids, zigzags, and abstract patterns whose meanings remain uncertain. Some researchers interpret them as symbolic representations of cosmological concepts. Others propose that they functioned as territorial markers, information systems, or mnemonic devices. A few have even suggested possible relationships to seasonal observations. No consensus exists. What is striking, however, is that such abstract imagery appears repeatedly across large areas of South America, hinting at intellectual traditions far more complex than once believed. Gabii is an ancient city located about 18 kilometers east of Rome in central Italy, yet its greatest mystery is not its age, but the possibility that some of the engineering principles later associated with Rome may have been developed here first. Excavations have revealed a remarkably organized urban landscape, advanced stoneworking techniques, sophisticated drainage systems, and evidence of large-scale planning dating back more than 2,500 years. The city flourished during the Iron Age and early Republican period, then gradually declined and was eventually abandoned. Unlike Rome, which was continuously rebuilt for centuries, Gabii remained relatively untouched after its collapse. As a result, archaeologists often describe it as a time capsule preserving a snapshot of urban technology from a critical stage in Mediterranean history. The site lies near the ancient volcanic basin of Lago di Castiglione in the Lazio region of Italy. Although classical writers such as Livy and Dionysius of Halicarnassus mentioned Gabii, systematic archaeological investigations only accelerated during the 20th and 21st centuries. One of the most important modern research programs, the Gabii project led by archaeologists from the University of Michigan, employed ground-penetrating radar, digital mapping, drone surveys, and large-scale excavation to reconstruct the city's layout. What researchers discovered challenged traditional assumptions about early urban development in central Italy. The first mystery concerns urban planning that appears far ahead of its time. Excavations revealed streets arranged according to a deliberate plan rather than the organic growth typically expected in early settlements. Major roads intersect at controlled angles and connect residential, industrial, and public areas in a manner resembling later Roman city planning. Some sectors display organized blocks, extending across large portions of the settlement. Urban planners today recognize that creating such a layout requires surveying knowledge, standardized measurements, and administrative coordination. Similar planning is known from Greek colonies and later Roman cities, yet Gabii demonstrates that comparable concepts existed in central Italy centuries earlier than many historians once believed. Archaeologists continue to debate whether this planning emerged independently, developed through interaction with neighboring cultures, or represented an early stage of the urban traditions that would later characterize Rome itself. The second mystery involves the enormous stone industry that supported the city's construction. Gabii sat atop extensive deposits of volcanic tuff, a relatively soft rock that hardens when exposed to air. The material became one of the most important building stones in ancient Latium. Ancient quarry faces surrounding the city reveal systematic extraction on a remarkable scale. Researchers estimate that hundreds of thousands of tons of stone were removed over centuries. Large blocks were cut with surprising precision, transported across uneven terrain, and assembled into buildings, roads, walls, and drainage systems. Even today, quarrying operations require logistical planning, workforce management, transportation networks, and quality control. Yet no surviving technical documents explain how Gabii organized such a vast operation. The stone itself survives, but the engineering system that produced it remains largely invisible. The third mystery centers on construction techniques that achieved extraordinary durability. Numerous structures at Gabii survived more than 2 millennia despite earthquakes, weathering, and human activity. Walls built from carefully fitted tough blocks continue to stand in recognizable form. Modern engineers studying ancient masonry often emphasize that stability depends on load distribution, foundation preparation, block geometry, and structural balance. The builders of Gabii clearly understood these principles through experience, even if they lacked formal mathematical descriptions. Similar mysteries appear at sites such as Machu Picchu, where precisely fitted stones resist seismic activity, and at ancient Greek temples whose foundations compensated for uneven terrain. Gabii belongs to this broader category of archaeological puzzles in which successful engineering is evident, but the methods behind it remain incompletely understood. The fourth mystery is hidden underground. Beneath the visible ruins lies a network of drainage channels and water management structures that demonstrate sophisticated hydraulic knowledge. Water was one of the greatest engineering challenges of the ancient world. Too little water threatened survival, while too much damaged buildings, roads, and farmland. Excavations have revealed channels carefully designed to control runoff and direct water away from inhabited areas. Maintaining proper flow requires understanding gradients and terrain. Modern drainage engineers rely on mathematical calculations and surveying equipment. Ancient builders possessed neither laser levels nor computerized models, yet many of their systems functioned effectively for centuries. Comparable achievements can be seen in Roman aqueducts, Persian qanats, and the hydraulic networks of Angkor in Cambodia. Gabii's underground infrastructure suggests that advanced water management existed in Latium long before Rome reached its engineering peak. The fifth mystery concerns standardized housing construction. Archaeologists identified neighborhoods where multiple buildings follow similar dimensions and layouts. This pattern suggests some form of planning or building standardization. Standardization is a hallmark of complex societies because it improves efficiency, simplifies construction, and facilitates maintenance. Ancient Rome eventually became famous for standardized military camps, roads, and public infrastructure. At Gabii, however, evidence indicates that certain forms of architectural standardization may have emerged centuries earlier. Researchers continue investigating whether these similarities reflect centralized planning, shared building traditions, economic constraints, or an organized administrative authority capable of coordinating large-scale construction projects. Another remarkable mystery involves the city's industrial capabilities. Excavations uncovered evidence of workshops, production zones, and economic activity integrated into the urban landscape. Ancient cities required constant supplies of tools, ceramics, building materials, and household goods. Maintaining such production demanded skilled labor, resource acquisition, transportation, and distribution systems. Comparisons with contemporary settlements suggest that Gabii functioned as more than a simple town. It operated as an economic center connected to regional trade networks throughout Latium. Yet many details of its industrial organization remain unknown. Archaeologists can identify production areas, but reconstructing the management systems behind them remains difficult because administrative records have not survived. The sixth mystery involves the relationship between Gabii and Rome. Ancient literary sources describe periods of rivalry, alliance, and cultural interaction between the two cities. Some traditions even claim that members of the Roman elite received education at Gabii. While such accounts are difficult to verify completely, archaeological evidence indicates substantial connections between the settlements. The possibility that technological, architectural, or administrative knowledge flowed from Gabii to Rome remains one of the most intriguing questions in early Italian history. Rome eventually became the largest city in the Mediterranean world, controlling an empire stretching across 3 continents. Yet during Gabii's peak, Rome was still developing. This chronological relationship raises a fascinating possibility. Some innovations later associated with Roman civilization may have roots in neighboring cities whose contributions were gradually forgotten. The seventh mystery concerns the city's sudden decline. By the imperial period, Gabii had lost much of its former importance. Population decreased, construction slowed, and major public projects ceased. Eventually, large portions of the city were abandoned. Archaeologists have proposed several explanations, including economic shifts, political centralization in Rome, changing trade routes, environmental pressures, and demographic decline. None fully explains the process. Similar mysteries surround the decline of many ancient centers, from the Maya cities of Central America to the Bronze Age settlements of the Eastern Mediterranean. Urban collapse rarely results from a single cause. Instead, it emerges from complex interactions among economic, environmental, and political factors. Gabii appears to fit this broader historical pattern, yet the precise sequence of events remains uncertain. Lalitgiri, isolated on a low hill range in Odisha, eastern India, appears at first glance to be another ruined Buddhist monastery. Yet beneath its weathered bricks lies one of the most puzzling engineering stories in ancient South Asia. Archaeologists uncovered evidence of a major Buddhist center dating from roughly the 1st century BC to the 13th century AD, making Lalitgiri one of the oldest Buddhist complexes in India. What transformed the site from an ordinary excavation into an archaeological mystery was not merely its age, but the discovery of advanced construction techniques, unusually durable materials, sophisticated planning, and perhaps most intriguingly, a series of stone relic caskets crafted with a level of precision that continues to raise questions about the technological capabilities of the people who built them. The modern rediscovery of Lalitgiri began during archaeological surveys of Odisha in the 20th century. Systematic excavations conducted by the Archaeological Survey of India eventually revealed a massive monastic complex, a large brick stupa, dozens of smaller votive stupas, sculptures, inscriptions, and one of the most important finds ever made at a Buddhist site in India. A relic chamber containing nested stone containers believed by some scholars to have held sacred Buddhist relics. As excavation expanded, researchers realized that Lalitgiri was not an isolated monastery. It formed part of a vast Buddhist network together with Ratnagiri and Udayagiri, creating a regional religious and educational landscape that flourished for centuries. Yet every new discovery seemed to generate even more difficult questions. The first puzzle emerges from the location itself. Lalitgiri occupies elevated terrain overlooking the surrounding plains. Modern visitors can reach the hill with relative ease, but transporting construction materials there nearly 2,000 years ago would have been a very different challenge. Archaeologists estimate that the principal stupa and associated structures required hundreds of thousands of bricks. Even if each brick weighed only 2 to 4 kilograms, the total mass of material transported uphill would have reached hundreds or even thousands of tons. Similar logistical challenges have been documented at sites such as Nalanda and Sanchi, but Lalitgiri presents an additional complication. Evidence suggests multiple phases of expansion over several centuries, meaning construction was not a single event but a continuous process requiring stable supply chains, labor organization, and engineering knowledge. No written records survive to explain how this logistical system operated. The durability of the brickwork presents another mystery. Many ancient brick structures across tropical South Asia have suffered severe deterioration from monsoon rains, biological growth, thermal stress and erosion. Yet substantial portions of Lalitgiri survived for more than a millennium. Laboratory analysis of ancient Indian bricks has demonstrated compressive strengths that sometimes approach or exceed those of certain modern fired bricks. Researchers believe ancient craftsmen carefully selected clay sources and controlled firing temperatures, but the exact production methods remain uncertain. Unlike modern brick manufacturing, which relies on standardized industrial kilns and temperature monitoring systems, ancient builders achieved remarkable consistency using technologies that remain only partially understood. The survival of these structures becomes even more impressive when compared with many later medieval buildings that deteriorated more rapidly despite having access to more advanced tools. Water management may represent an even greater engineering achievement. Odisha receives significant seasonal rainfall, often exceeding 1,400 millimeters annually. Any large hilltop complex exposed to centuries of monsoon activity faces constant threats from runoff, erosion, and foundation instability. Modern engineers combat such problems using drainage calculations, hydrological models, and reinforced foundations. Lalitgiri's builders possessed none of these technologies, yet the archaeological record indicates that the site remained functional through countless monsoon cycles. Excavations have identified drainage channels and evidence of carefully planned water control systems, but researchers still struggle to reconstruct the complete hydraulic network. The unanswered question is whether surviving features represent only a small fraction of a much larger engineering system that has since disappeared. The mystery becomes deeper when examining the broader architectural planning of the complex. The layout of monasteries, shrines, pathways, and stupas suggests deliberate organization rather than gradual random growth. Ancient builders appear to have balanced religious symbolism with practical concerns such as circulation, visibility, drainage, and structural stability. Comparable planning can be observed at major Buddhist centers like Nalanda, yet Lalitgiri's elevated terrain imposed additional constraints. Modern archaeological mapping reveals alignments and spatial relationships that imply careful surveying methods. The challenge is understanding how such measurements were performed. Without modern optical instruments, laser levels, or standardized engineering equipment, ancient surveyors still managed to create a coherent architectural landscape capable of functioning for centuries. Among all these mysteries, however, none is more fascinating than the relic caskets discovered within the stupa complex. These objects transformed Lalitgiri from an important archaeological site into a genuine technological puzzle. The relic chamber contained multiple nested containers fashioned from stone with remarkable craftsmanship. At first glance, the caskets appear simple. Closer examination reveals an extraordinary degree of precision. The surfaces were carefully shaped and smoothed. The lids fit their bases with striking accuracy. Symmetry is maintained across multiple components. Internal cavities were hollowed with controlled dimensions while preserving structural integrity. Even more remarkable, these achievements were accomplished using technologies available nearly 2,000 years ago. To appreciate the challenge, It is useful to compare the relic caskets with other ancient precision stonework. Egyptian craftsmen produced finely finished granite sarcophagi. Roman artisans carved marble sculptures with astonishing detail. Indian stoneworkers created the polished pillars of Emperor Ashoka and the rock-cut architecture of Ajanta and Ellora. Yet each of these projects required highly specialized knowledge, sophisticated toolkits, and generations of accumulated expertise. The relic caskets of Lalitgiri belong within this broader tradition of precision craftsmanship, but their existence raises a difficult question. Why invest such extraordinary effort into objects that would remain hidden inside a sealed stupa? Microscopic examination suggests controlled shaping and finishing techniques that required exceptional skill. Stone is an unforgiving material. Remove too much and the piece is ruined. Apply uneven force and fractures can develop. Achieve symmetry on one surface but not another, and the final object becomes visibly imperfect. Modern machinists solve these problems with calibrated tools and measurement devices. Ancient artisans relied on experience, templates, abrasives, and techniques that remain poorly documented. The finished caskets demonstrate not only artistic ability, but also a practical understanding of geometry, material behavior, and manufacturing control. The nested arrangement of the containers introduces another layer of complexity. Multiple vessels were designed to fit within one another, while maintaining dimensional compatibility. This implies planning before fabrication began. Each container had to be produced according to measurements that allowed the complete assembly to function as intended. Similar engineering logic appears in modern precision manufacturing, where components must meet predetermined tolerances. Whether ancient craftsmen thought in terms comparable to modern tolerances remains unknown, yet the physical evidence suggests they achieved remarkably accurate results. The mystery goes beyond craftsmanship. Creating these relic caskets required skilled artisans, training systems, workshops, tools, and resources. While the finished objects remain, the knowledge and infrastructure behind them disappeared centuries ago. Rising above the Quebrada de Humahuaca Valley in Jujuy province, at an elevation of approximately 2,465 meters, the settlement controlled one of the most important transportation corridors in the southern Andes. Archaeologists estimate that the site covered more than 15 hectares and contained hundreds of stone structures, storage facilities, defensive walls, ceremonial spaces, and residential districts. Built by the Omaguaca people around the 10th century CE and occupied until the Spanish conquest in the 16th century, Pucara de Tilcara remains one of the most remarkable examples of ancient engineering in South America. Yet the greatest mystery is not what survives today. The greatest mystery is how its builders acquired and applied sophisticated knowledge of military engineering, water management, logistics, and construction without leaving behind written explanations. Pucara de Tilcara is located in the Quebrada de Humahuaca, a narrow mountain valley carved by the Rio Grande in northwestern Argentina. The site became known to modern archaeology during the late 19th century, but systematic investigations began in 1908 when archaeologists Juan Bautista Ambrosetti and Salvador de Benedetti conducted extensive excavations. Their work revealed a large, fortified settlement occupying a strategic hill overlooking the valley below. Over the following decades, researchers uncovered residential compounds, defensive structures, agricultural features, storage facilities, burial areas, and evidence of long-distance trade. The discoveries transformed understanding of pre-Hispanic societies in the southern Andes and demonstrated that the region supported highly organized communities centuries before European arrival. The first mystery begins with geography. The fortress occupies a position that appears almost purpose-built for defense. From the summit, observers could monitor movement through large sections of the valley while controlling access to important trade routes linking the central Andes with lower regions farther south. Modern military historians often compare the importance of terrain selection to the placement of medieval European castles or Roman frontier forts. The builders of Pucara de Tilcara seem to have understood these principles centuries before similar concepts were formally documented in military science. The mystery is how they achieved such precision. Without modern surveying instruments, topographic maps, aerial photography, or satellite imagery, the builders identified a location that maximized visibility, defense, and control of transportation corridors simultaneously. Researchers have proposed that generations of accumulated geographic knowledge allowed the community to evaluate strategic positions with remarkable accuracy. Yet no one knows precisely how this knowledge was transmitted or organized. The fortress demonstrates a level of military planning far beyond what many people traditionally associate with pre-Columbian societies. Constructing hundreds of buildings on a steep rocky hill presented enormous engineering challenges. Unlike settlements established on flat plains, Pucara de Tilcara required extensive modification of natural terrain. Builders created artificial terraces, leveled construction platforms, stabilized slopes, and integrated architecture directly into the mountain landscape. Many structures were built using local stone without mortar. Despite centuries of weathering, earthquakes, and erosion, significant portions of the foundations remain intact. The achievement becomes even more impressive when compared with other ancient mountain settlements. Machu Picchu in Peru is famous for its terrace engineering and slope stabilization systems. Pucara de Tilcara demonstrates similar principles on a smaller scale, but under very different cultural conditions. Modern geotechnical engineers understand how slope failure occurs. They calculate load distributions, drainage patterns, and soil stability using advanced software. The Omaguaca possessed none of these technologies, yet they produced a settlement capable of surviving for centuries. How they developed this understanding remains only partially understood. Water represented one of the greatest challenges facing any settlement in the semi-arid Andes. Average rainfall in parts of the region can fluctuate dramatically from year to year. Seasonal variation creates periods of abundance followed by periods of scarcity. A large population could not survive without reliable water management. Archaeological evidence suggests that the inhabitants developed systems for collecting, directing, storing, and distributing water. However, only fragments of these systems survive. This creates a major mystery. How did thousands of people maintain a permanent settlement on an elevated hilltop where natural water access was limited? Researchers studying ancient Andean hydraulic systems often compare them to sophisticated water management networks developed by the Inca centuries later. Some scholars believe that knowledge preserved within local traditions may have contributed to later engineering developments across the Andes. The exact design of the original hydraulic infrastructure remains uncertain, leaving one of the most important technological questions unanswered. Perhaps the least visible engineering achievement at Pucara de Tilcara involved food preservation. Excavations revealed numerous storage structures capable of holding agricultural products for extended periods. Maintaining food supplies was essential because the fortress population needed protection against drought, crop failures, and military threats. The challenge was immense. Stored maize, quinoa, and other crops had to remain edible despite temperature fluctuations, insects, moisture, and microbial contamination. Modern storage facilities rely on controlled ventilation, humidity monitoring, and scientific understanding of spoilage processes. Ancient communities lacked these tools, yet evidence indicates that large-scale storage operated successfully. Some researchers suspect that architectural placement exploited prevailing winds to improve passive ventilation. Similar principles appear in ancient granaries across the Mediterranean and Middle East. Whether the Oumuagwaka independently discovered comparable solutions remains unknown. The surviving ruins suggest a sophisticated understanding of environmental control, but the details remain largely invisible. Pucara de Tilcara did not exist in isolation. Numerous archaeological sites throughout the Quebrada de Humahuaca indicate the presence of interconnected communities occupying strategically important locations. Several hilltops maintain direct lines of sight with one another. This has inspired a fascinating hypothesis. Researchers propose that visual communication systems may have linked settlements across the valley. Smoke signals, beacon fires, reflective surfaces, or other signaling methods could have transmitted warnings rapidly over long distances. History provides many parallels. The Roman Empire operated extensive beacon networks. Ancient China used signal towers along frontier defenses. Byzantine fortifications transmitted messages across mountainous terrain using fire signals. If similar systems existed here, communities could have shared information far faster than messengers traveling on foot. The problem is that communication technologies often leave little archaeological evidence. The theory remains plausible, but definitive proof has not yet been found. Northwestern Argentina lies within a tectonically active region influenced by the ongoing uplift of the Andes. Earthquakes have affected the area throughout history. Despite this reality, many structures at Pucara de Tilcara survived long enough for archaeologists to study them centuries later. Some specialists argue that the use of relatively small stones may have increased structural flexibility. Instead of resisting seismic forces through rigidity, the walls may have absorbed movement through numerous joints between individual stones. This principle resembles certain earthquake-resistant construction techniques observed elsewhere in the Andes. The comparison becomes especially interesting when examining Inca architecture. Although the construction methods differ, both traditions appear to emphasize stability through adaptive structural behavior rather than massive rigid walls. Whether the builders consciously understood seismic engineering or simply refined successful methods through generations of observation remains unknown. Either explanation implies a remarkable body of practical knowledge. A settlement of this size required more than engineering, it required organization. Archaeologists have discovered evidence of trade involving materials that originated far beyond the immediate region. Exotic goods, ceramics, and exchange networks connected the community to broader economic systems operating throughout the Andes. The logistical implications are extraordinary. Hundreds or perhaps thousands of people required food, tools, construction materials, and social coordination. Large labor projects demanded planning. Defensive infrastructure required maintenance. Agricultural production had to support both residents and specialists. Modern economists often analyze cities through models of resource distribution and labor management. Applying similar reasoning to Pucara de Tilcara reveals a surprisingly complex system operating without written bureaucratic records. The physical infrastructure survives, but the administrative mechanisms do not. This creates one of the most intriguing mysteries of all. Mughal lies in the coastal plains of West Bengal, India. Beneath ordinary farmland near the town of Dantan, archaeologists uncovered the remains of a forgotten Buddhist center, whose engineering achievements continue to raise questions today. The modern rediscovery of Mughal was surprisingly recent. Although local villagers had long known about ancient bricks emerging from the ground after seasonal rains, systematic archaeological excavations only began in 2003. What researchers expected to find was a modest monastic complex dating to the early medieval period. What emerged instead was evidence of a large Buddhist institution that flourished between roughly the 6th and 12th centuries CE, during a time when Eastern India was one of the intellectual centers of the Buddhist world. Massive brick structures, elaborate terracotta decorations, monastic cells, courtyards, and religious architecture gradually appeared beneath centuries of accumulated soil. Yet the more archaeologists uncovered, the more difficult it became to explain how such a sophisticated complex could survive, function, and prosper in an environment that seems fundamentally hostile to long-term preservation. The first puzzle begins with the location itself. Mukalmari sits in a low-lying region influenced by monsoon rains, seasonal flooding, humidity, and fluctuating groundwater levels. Modern engineers recognize these conditions as particularly destructive for masonry architecture. Water infiltration weakens foundations, salts crystallize inside bricks, biological growth accelerates deterioration, and repeated wet-dry cycles gradually destroy structures. Yet substantial portions of Mukalmari survived for nearly a millennium after abandonment. This immediately raises questions about the knowledge possessed by its builders. Either they understood local geology and hydrology far better than previously assumed, or they employed construction techniques that have largely disappeared from the historical record. Excavations revealed extensive brick architecture characterized by remarkable consistency. Many ancient civilizations produced bricks, but Mukalmari's bricks demonstrate a level of standardization that suggests carefully controlled manufacturing processes. Archaeologists measured numerous bricks and found recurring dimensions throughout different sections of the complex. Standardization on this scale is not merely aesthetic, it reflects organization, quality control, and production systems capable of maintaining uniformity across thousands of construction elements. Similar patterns can be observed at Nalanda and other major Buddhist institutions of Eastern India. Yet the exact methods remain uncertain. Researchers can analyze surviving bricks chemically, but they still cannot fully reconstruct how ancient craftsmen consistently achieved such durable materials using technologies available more than 1,000 years ago. The durability itself presents another mystery. Modern fired bricks commonly experience significant deterioration within decades when exposed continuously to tropical environments without maintenance. Mukalmari's bricks endured centuries of monsoon conditions. Laboratory studies of ancient South Asian bricks often reveal firing temperatures between 700 and 1,000 degrees Celsius, depending on the clay composition and kiln design. Achieving and maintaining such temperatures consistently across large production batches would have required sophisticated control of fuel, airflow, and kiln structure. No surviving technical manuals describe these processes. The knowledge appears to have vanished while the products themselves remained. Yet perhaps the most astonishing discoveries at Mukalmari are neither its walls nor its foundations. They are the terracotta plaques that once decorated the monastery. These artifacts represent one of the most remarkable examples of artistic and technical craftsmanship in early medieval India, and they continue to challenge researchers attempting to understand how they were produced. At first glance, the plaques appear to be decorative elements depicting Buddhist figures, celestial beings, floral motifs, geometric patterns, animals, and scenes from religious traditions. Closer examination reveals something far more impressive. Individual details sometimes measure only a few millimeters across. Facial expressions remain recognizable. Jewelry patterns display extraordinary precision. Fabric folds, hair arrangements, and ornamental borders exhibit a complexity that rivals much later artistic traditions. Under magnification, many surfaces reveal astonishing levels of refinement despite being created from clay rather than stone or metal. The obvious question is how such consistency was achieved. If each plaque was sculpted entirely by hand, the labor investment would have been enormous. Hundreds of plaques have been recovered, many displaying remarkably similar proportions and stylistic characteristics. This has led some researchers to suggest the use of molds or semi-standardized production techniques. However, the mystery does not end there. Even if molds were used, the molds themselves would have required master artisans capable of producing extraordinarily detailed prototypes. Furthermore, the firing process had to preserve delicate features without warping or cracking. Clay naturally shrinks during drying and firing. Maintaining geometric accuracy across large numbers of plaques would have required precise control over material composition and manufacturing procedures. Comparisons with other ancient civilizations make the achievement even more remarkable. Roman terracotta decorations often emphasized repetition and large-scale architectural ornamentation. Chinese ceramic traditions mastered high-temperature firing and detailed artistic production. Yet Mughalmari demonstrates a unique combination of religious symbolism, mass production, and miniature precision. Some decorative elements are so detailed that modern reproductions frequently require magnification tools and highly controlled workshop environments to achieve the comparable results. The ancient craftsmen accomplished this without modern measurement devices, electric kilns, or industrial manufacturing systems. The distribution of the plaques also raises questions about organization. Creating a few exceptional artworks is one thing. Producing hundreds of sophisticated decorative elements for a large architectural complex is another. Such output implies specialized workshops, trained artisans, supply chains for clay procurement, fuel acquisition, quality control, and possibly even apprenticeship systems. Very little direct evidence of these industrial processes survives. Archaeologists can observe the final products, but only partially reconstruct the organizational structures that made them possible. The mystery extends beyond art into information management. During its peak, Mughalmari was likely connected to major Buddhist networks stretching across eastern India and beyond. The monastery existed during a period when institutions such as Nalanda attracted students and scholars from multiple regions of Asia. Trade routes connected Bengal to Sri Lanka, Southeast Asia, and other parts of the Indian Ocean world. Such connections suggest that Mughalmari may have participated in extensive exchanges of ideas, texts, technologies, and religious practices. Yet almost none of the manuscripts that once existed have survived. Tropical climates are notoriously destructive to organic materials. Palm leaf manuscripts, wooden objects, textiles, and administrative records disappear rapidly without exceptional preservation conditions. What remains is architecture without its library, decoration without its documentation, and engineering without its instruction manuals. Water management presents another unresolved challenge. Any large monastic institution housing dozens or even hundreds of residents required reliable systems for drinking water, sanitation, drainage, and flood control. Modern archaeological surveys have identified certain structural features that may have played roles in water regulation, but a complete hydraulic picture remains elusive. This is surprising because long-term occupation would have been impossible without effective environmental management. The absence of clearly preserved infrastructure leaves researchers wondering whether major components remain buried beneath unexcavated areas, or whether perishable engineering solutions have vanished completely. Even the scale of Mughalmari remains uncertain. Only portions of the site have been excavated. Geophysical surveys and surrounding topography suggest that additional structures may still lie hidden underground. If future excavations reveal larger sections of the complex, current interpretations could change dramatically. Similar situations occurred at major archaeological sites across South Asia, where initial discoveries represented only a fraction of the original settlement. Every new trench at Mughal carries the possibility of uncovering evidence that reshapes our understanding of the monastery's size, function, and technological sophistication. El Xincal is one of the most mysterious Inca cities ever built outside Peru. Located in the Quimiville Valley of Catamarca Province, northwestern Argentina, the site lies more than 1,500 kilometers south of Cusco, the capital of the Inca Empire. Yet despite this enormous distance, archaeologists discovered a city planned according to core Inca principles, complete with a monumental ceremonial plaza, a sacred Ushnu platform, terraced hills, administrative buildings, storage facilities, and connections to the vast Chapak-Nan road network. The greatest mystery is not that the city existed, but how Inca engineers successfully recreated a sophisticated imperial center so far from the heart of their civilization while employing technologies that remain only partially understood today. The ruins became known to modern researchers during the 19th century, but systematic archaeological investigations expanded significantly during the 20th century under Argentine scholars, including Alberto Rex Gonzalez and subsequent research teams. Excavations revealed that El Xincal was likely founded during the late 15th century, possibly under the expansion campaigns of Tupac Inca Yupanqui or Huayna Capac. Covering roughly 30 hectares, the settlement quickly emerged as one of the most important Inca administrative centers in southern South America. Yet every major discovery seemed to create new questions rather than provide answers. One of the greatest engineering mysteries concerns the decision to build El Xincal itself. Most empires lose administrative control as distance increases because communication slows, transportation becomes difficult, and logistics become increasingly complex. The Roman Empire experienced these challenges, and the Han dynasty faced similar limitations. Yet the Incas successfully established a highly organized center more than 1,500 kilometers from Cusco. Without wheeled transport, iron tools, horses, or written bureaucratic records comparable to those used in Eurasian civilizations, the Inca somehow maintained authority across an empire stretching approximately 4,000 kilometers along the Andes. El Xincal demonstrates that this system worked remarkably well. Archaeologists have identified architectural layouts closely resembling those found near Cusco itself, and the precision of this replication suggests centralized planning, standardized construction methods, and highly effective communication networks. The exact mechanisms that allowed such control remain debated. Modern comparisons help illustrate the scale of this achievement. The distance separating El Xincal from Cusco is comparable to the distance between Paris and Athens, and maintaining administrative cohesion across such territory without modern communication technologies would challenge even many pre-industrial states. Perhaps the most fascinating mystery involves astronomical engineering. Several studies indicate that the city's orientation was not random. The central plaza, ceremonial structures, and surrounding sacred hills appear to interact with solar movements throughout the year. Researchers have proposed that the two prominent terraced hills flanking the city may have served as astronomical reference points. This pattern appears elsewhere in Inca architecture. Machu Picchu, Cusco, and numerous ceremonial centers contain alignments associated with solstices and equinoxes, and El Xincal seems to belong to the same tradition. The engineering challenge is significant because determining precise solar positions requires long-term observation. Modern surveyors rely on compasses, GPS systems, laser instruments, and computer models, yet Inca engineers possessed none of these technologies. Nevertheless, they achieved alignments accurate enough to remain recognizable centuries later. Some archaeologists argue that repeated observations conducted over generations allowed Inca specialists to construct reliable astronomical calendars. Others suggest that sophisticated surveying techniques may have existed but disappeared after the Spanish conquest. No definitive explanation has been established. At the center of El Xincal stands a monumental Ushnu platform. Similar structures appear throughout the Inca world, but El Xincal preserves one of the best examples discovered outside Peru. The structure appears deceptively simple, yet its position dominates the entire city. From its elevated surface, observers could view major sections of the settlement as well as surrounding natural landmarks. The mystery concerns its exact purpose. Some researchers interpret the Ushnu as a ceremonial platform used during state rituals. Others argue that it functioned as an astronomical observation point. A third hypothesis suggests that it served both political and scientific purposes simultaneously. Measurements indicate that several sightlines from the platform correspond with significant landscape features. Whether these alignments were symbolic, astronomical, administrative, or all three remains uncertain. The situation resembles debates surrounding Stonehenge in Britain and Chanquillo in Peru, where monumental structures often survive while the knowledge explaining their precise function disappears. El Xincal was not built on naturally flat ground. The settlement occupies a landscape of uneven terrain, surrounded by hills and seasonal watercourses. To create the city's organized appearance, builders modified large portions of the natural environment. Terraces were constructed, slopes were stabilized, drainage systems were established, public spaces were leveled, and ceremonial hills were reshaped. Such work required extraordinary quantities of labor. Modern engineers would employ bulldozers, excavators, grading equipment, and surveying instruments, whereas the Inca relied primarily on stone tools, wooden implements, rope, and human labor. Researchers estimate that major Inca construction projects often involved thousands of workers organized through the Emitir labor system. Yet the methods used to coordinate earth-moving operations at El Xincal remain poorly documented. The city demonstrates landscape engineering on a scale comparable to agricultural terracing systems elsewhere in the Andes, some of which moved hundreds of thousands of cubic meters of material. El Xincal may represent a similar achievement in urban planning. Water determined survival throughout the Andes. Although El Xincal receives more rainfall than many desert regions controlled by the Inca, seasonal fluctuations still created challenges. Archaeologists have identified evidence of channels, drainage features, and hydraulic planning integrated into the city's layout. The mystery lies in the sophistication of these systems. Throughout the Inca world, engineers designed water networks capable of functioning for centuries. Machu Picchu contains drainage systems that continue to operate today, while Tipon near Cusco preserves hydraulic works that remain remarkably efficient despite being more than 500 years old. El Xincal appears to have incorporated similar principles. Engineers successfully controlled runoff, protected buildings from erosion, and supplied water to critical areas of the settlement. Yet many hydraulic components remain buried or poorly understood, and future excavations may reveal a far more complex system than currently recognized. El Xincal was connected to the Hapak Nan, the vast Inca road system extending across western South America. This network exceeded 30,000 kilometers in total length. By comparison, many major Roman roads collectively covered similar scales across Europe and the Mediterranean. The mystery is how the Inca maintained such a system without wheeled transport. Messengers known as chasqui carried information between relay stations. Goods moved through coordinated labor networks, and administrative commands traveled across mountains, deserts, and valleys. El Xincal functioned as one of the southern hubs within this immense infrastructure system. Modern logistical models suggest that maintaining reliable communication across thousands of kilometers without written dispatches should have been extremely difficult. Yet the archaeological evidence demonstrates that the system operated successfully for generations. Exactly how information, taxation records, labor obligations, and political decisions were coordinated remains one of the greatest unanswered questions in Inca studies. Only a portion of El Xincal has been thoroughly investigated. Excavations have revealed plazas, administrative compounds, ceremonial structures, and residential areas. However, large sections remain unexplored. This creates a fascinating possibility. The visible city may represent only a fraction of the original settlement. Ground-penetrating radar surveys at archaeological sites around the world have repeatedly revealed hidden architecture invisible from the surface. Similar discoveries transformed understanding of Angkor in Cambodia, Teotihuacan in Mexico, and numerous Roman cities throughout Europe. If comparable investigations are conducted extensively at El Xincal, researchers may uncover additional roads, workshops, storage facilities, elite residences, or hydraulic structures. Such discoveries could fundamentally change current interpretations of the site. Located on the edge of the Abalessa oasis in southern Algeria, deep within the central Sahara near the Hogga Mountains, the tomb of Tin Hinan remains one of North Africa's most intriguing archaeological mysteries. In 1925, a French archaeological expedition opened the massive stone mausoleum traditionally linked to Tin Hinan, the legendary ancestral queen of the Tuareg people. Inside, researchers uncovered the remains of a woman buried with gold jewelry, silver ornaments, glass objects, and artifacts connected to the Roman world. The discovery immediately sparked questions that remain unresolved nearly a century later. The mystery extends beyond the identity of Tin Hinan herself. More puzzling is how such a sophisticated stone monument could have been designed, supplied, and constructed in one of the most unforgiving environments on Earth. Modern archaeology can measure the tomb, analyze its materials, and date many of its contents. Yet it still struggles to explain the engineering systems, logistical networks, and technical knowledge that made the monument possible. The mausoleum itself is an architectural anomaly. Built from carefully arranged stone blocks, the structure contains multiple chambers connected through a planned internal layout. Archaeological surveys have documented 11 separate rooms, organized within a rectangular complex measuring roughly 26 meters in length. While this size may seem modest compared with the pyramids of Egypt or the imperial tombs of China, the challenge lies in its location rather than its dimensions. The Sahara is not simply a desert, it is the largest hot desert on Earth, covering approximately 9 million square kilometers. Summer temperatures frequently exceed 45 degrees Celsius. Annual rainfall can fall below 50 millimeters in many regions, and water sources are often separated by hundreds of kilometers. Every stone transported, every worker fed, and every construction activity organized required logistical solutions that remain largely invisible in the archaeological record. One of the first mysteries concerns the sourcing and movement of construction materials. Researchers have identified local stone sources around the Hoggar region, but identifying a quarry is only the beginning of the problem. The builder still needed to extract, shape, transport and precisely position large quantities of stone without wheeled transport systems comparable to those used in later civilizations. Similar questions have been raised at sites such as Stonehenge in Britain, where some stones travelled over 200 kilometres, and at the Yangshan Quarry in China, where unfinished megaliths demonstrate the enormous difficulty of moving massive stone blocks. Tin Hinan's builders faced an additional obstacle: desert terrain. Sand dramatically increases friction, reducing transport efficiency. Even modern military logistics treat desert operations as exceptionally difficult. Yet ancient builders succeeded in creating a durable monument that survived for more than 16 centuries. The geometric organization of the tomb presents another puzzle. Archaeologists have noted that the chambers follow a coherent architectural plan rather than an organic accumulation of rooms. This implies surveying methods capable of maintaining alignment, spacing, and structural stability. Modern surveyors rely on optical instruments, laser measurements, satellite positioning, and digital modeling. Ancient builders possessed none of these tools. Nevertheless, they achieved results that suggest careful measurement and planning. Similar questions arise at Roman military camps, Egyptian temples, and Inca settlements. Across the ancient world, accurate geometry repeatedly appears long before the invention of modern engineering mathematics. Tin Hinan tomb belongs to this broader pattern, yet the exact techniques used by its builders remain unknown. The burial chamber itself introduces one of the most debated technical mysteries. The woman's remains were discovered in a remarkably preserved state considering the age of the tomb. Sahara conditions undoubtedly contributed to preservation, but environmental factors alone may not fully explain the phenomenon. The internal design of the structure appears to have created a stable microclimate. Temperature fluctuations, airflow, humidity levels, and chamber orientation all influence preservation rates. Today, museums spend millions of dollars controlling these variables through climate-controlled systems. The possibility that ancient builders unintentionally or deliberately created similar environmental stability raises intriguing questions about empirical knowledge accumulated through generations of observation. The artifacts found within the tomb reveal an even larger mystery extending far beyond the structure itself. Archaeologists recovered gold bracelets, silver jewelry, glass objects, and a Roman coin believed to date to the reign of Emperor Constantine during the 4th century CE. Such discoveries demonstrate that Abalessa was connected to networks extending across thousands of kilometers. Trade routes linked North Africa, the Mediterranean coast, the Sahara, and sub-Saharan Africa long before modern roads existed. Maintaining these routes required sophisticated navigation, resource management, and communication systems. A caravan crossing the Sahara often traveled hundreds or even thousands of kilometers between major population centers. Water availability determined survival. A single navigational error could prove fatal. Yet trade flourished for centuries. The existence of imported luxury goods in Tin Hinan's tomb indicates that these logistical systems operated with remarkable efficiency. Some historians compare Sahara trade networks to maritime shipping lanes. Both required detailed environmental knowledge, reliable routes, predictable stopping points, and organizational structures capable of coordinating long-distance movement. The difference is that sailors navigated oceans, while Saharan traders crossed landscapes that often appeared featureless. Modern satellite imagery reveals ancient caravan routes threading across the desert like invisible highways. Many were established centuries before Tin Hinan's lifetime. The engineering challenge was not constructing roads, but maintaining navigational knowledge across generations. How this information was preserved remains only partially understood. Debate also surrounds the age of the monument itself. Most researchers place the burial in the 4th or 5th century CE based on associated artifacts. However, some scholars have suggested that the structure may have undergone multiple phases of use. Architectural modifications visible in certain sections hint at possible additions or renovations. Similar patterns appear at royal tombs throughout the ancient world. Egyptian pyramids often incorporated earlier structures. Roman buildings frequently reused older foundations. In the Andes, successive cultures repeatedly rebuilt ceremonial centers over existing sacred locations. If Tin Hinan Tomb followed a comparable pattern, parts of the structure could potentially be older than the burial itself. Evidence remains inconclusive, but the possibility continues to attract scholarly interest. The identity of Tin Hinan presents another layer of uncertainty. Tuareg oral traditions describe her as a founding queen who migrated into the Ahaga region and became the ancestral mother of important Tuareg lineages. Oral traditions can preserve historical information across surprisingly long periods. Modern research into Polynesian navigation, indigenous Australian traditions, and African oral histories has demonstrated that some narratives retain accurate memories for centuries. Yet separating historical fact from symbolic mythology remains difficult. Genetic studies conducted on the remains have generated additional debate regarding ancestry and population movements in the Sahara. Instead of resolving the mystery, scientific analysis has often complicated it by revealing evidence of cultural interactions across vast regions. Kardaki Temple is one of the strangest ancient Greek temples ever discovered. Standing on the island of Corfu in western Greece, overlooking the Ionian Sea, the structure appears at first glance to be a typical archaic Greek sanctuary. Yet the deeper archaeologists investigate its remains, the more unusual it becomes. Built around the 6th century BCE, Kardaki challenges some of the fundamental assumptions about how Greek temples were designed and constructed. Even today, more than 2,500 years later, researchers continue debating why its builders abandoned architectural conventions followed throughout the Greek world and how they achieved a level of geometric precision that remains difficult to fully explain. The temple became known to modern archaeology in the early 19th century when portions of the structure were identified near the famous Kardaki Spring on Corfu. Excavations revealed the foundations and architectural fragments of an ancient temple that differed significantly from other Greek sanctuaries of the same era. What initially appeared to be a routine archaeological discovery gradually evolved into a puzzle involving engineering, geometry, geology, and lost architectural knowledge. The first mystery concerns the temple's highly unusual architectural design. Most Greek temples built during the Archaic period followed established Doric conventions. Structures such as the Temple of Hera at Olympia and the early temples at Paestum incorporated triglyphs and metopes as part of the characteristic Doric entablature. Kardaki, however, appears to have omitted these features entirely. This may seem like a minor decorative difference, but from an engineering perspective it is significant. Triglyphs and metopes were not merely ornamental, they formed part of a structural system that distributed loads from the roof into the supporting columns below. The absence of these elements raises difficult questions. Did Kardaki represent an experimental architectural tradition? Was it influenced by Ionic construction techniques? Or did its builders possess a local engineering method that disappeared from history? Some scholars have suggested that Kardaki may represent one of the earliest examples of architectural innovation that blurred the distinction between the Doric and Ionic orders. If true, the temple provides evidence that ancient Greek architecture evolved through experimentation rather than strict adherence to established formulas. The second mystery involves the temple's location. Kardaki was constructed immediately beside a natural spring. Modern engineers generally avoid placing massive stone structures on water-saturated ground because groundwater can destabilize foundations through erosion, settlement, and seasonal movement. Yet the temple survived for centuries in precisely such an environment. Hydrological studies demonstrate that groundwater significantly affects soil mechanics. When water content increases, the bearing capacity of many soils decreases, creating conditions that can lead to uneven settlement. Ancient builders obviously lacked modern geotechnical instruments, yet Kardaki's foundations appear to have been sufficiently stable to support a substantial stone structure for generations. How did they evaluate the ground conditions? Did they understand subsurface drainage? Did they incorporate hidden foundation systems now lost to erosion? Similar questions surround other ancient sites located near water sources, including certain sanctuaries at Delphi and Didyma. Kardaki suggests that Greek builders possessed practical geological knowledge that was never formally recorded. The third mystery concerns the transportation and assembly of construction materials. Although the temple was built primarily from local limestone, moving large stone blocks remained a formidable engineering challenge. Individual architectural elements may have weighed several tons. Without cranes, hydraulic machinery, or iron industrial equipment, ancient builders relied entirely upon human labor, animals, ropes, timber frameworks, and mechanical principles. Experimental archaeology has shown that teams using ropes and wooden sledges can move stones weighing multiple tons. However, successfully transporting, lifting, positioning, and aligning hundreds of architectural components requires extraordinary organization. Researchers studying Greek temple construction often compare these achievements with those of Egyptian pyramid builders and Roman engineers. In every case, the surviving monuments demonstrate capabilities far beyond what many people assume was possible in antiquity. The fourth mystery involves seismic resilience. Corfu lies within a tectonically active region, influenced by interactions between the African and Eurasian plates. Throughout historical time, Greece has experienced numerous significant earthquakes. Modern seismic hazard maps continue to classify portions of the region as vulnerable to strong ground motion. Yet portions of Kardaki's foundation survived despite centuries of seismic activity. This raises the possibility that ancient builders unintentionally, or perhaps intentionally, incorporated features that improved earthquake resistance. Similar discussions surround the Parthenon in Athens, whose precisely fitted stone blocks help dissipate stress during seismic events. Some engineers have noted that ancient Greek masonry occasionally behaved as a flexible system rather than a rigid one. If Kardaki employed comparable principles, it may represent an early example of earthquake-aware construction. The fifth mystery is perhaps the most astonishing of all: the temple's extraordinary geometric precision. When archaeologists analyzed the surviving foundations and column spacing, they discovered evidence of remarkable proportional consistency. Distances between structural elements appear to follow carefully planned mathematical relationships. The builders were not simply stacking stones, they were implementing a geometric design with impressive accuracy. This achievement becomes even more remarkable when viewed in historical context. The temple was constructed approximately 2,600 years ago. There were no laser levels, no electronic surveying instruments, no computer modeling software, and no modern measurement devices. Yet the builders succeeded in creating a structure whose dimensions remained internally consistent across the entire layout. Modern surveys of Greek temples frequently reveal surprisingly small construction errors. In some cases, deviations are measured in mere centimeters across structures extending tens of meters. At the Parthenon, for example, researchers have documented sophisticated geometric refinements, including subtle curvature and optical corrections designed to create visual perfection. Kardaki may represent an earlier manifestation of the same intellectual tradition. The central question is simple: how did they achieve such precision? Ancient Greek surveyors likely employed ropes, measuring rods, plumb bobs, sighting instruments, and geometric procedures derived from practical mathematics. Yet the exact methods used at Kardaki remain unknown. No construction manuals survive. No engineering drawings have been discovered. No inscriptions explain the procedures used by the architects. The precision visible in the surviving remains implies a deep understanding of geometry. To establish accurate right angles, maintain proportional relationships, and align structural elements consistently, builders required reliable measurement systems and highly trained specialists. Such expertise does not emerge spontaneously. It develops through generations of accumulated technical knowledge. Comparisons with other ancient civilizations make Kardaki even more intriguing. Egyptian pyramid builders aligned monuments with astonishing accuracy. Roman engineers constructed aqueducts that maintained gradients of only a few centimeters per kilometer. The creators of the Antikythera mechanism manufactured precision bronze gears more than 2,000 years ago. Kardaki belongs within this broader pattern of ancient technological achievement. It demonstrates that sophisticated engineering often existed long before the appearance of modern scientific instruments. The sixth mystery concerns the temple's religious purpose. Despite decades of study, archaeologists remain uncertain which deity the sanctuary was dedicated to. Various proposals have linked the temple to Apollo, Artemis, or Poseidon, but definitive evidence remains absent. This uncertainty complicates attempts to understand why the structure was built in such an unusual manner. Religious requirements often influenced architectural design in the ancient world. Without knowing the temple's exact function, researchers lack an important piece of the puzzle. Dir Kathar lies in the forested hills of Madhya Pradesh in central India. Scattered across a quiet landscape are the remains of more than 30 ancient Buddhist stupas dating back over 2,000 years. At first glance, the site appears modest compared to famous monuments such as Sanchi. Yet the deeper archaeologists investigated Dir Kathar, the more they encountered a mystery hidden not in legends or lost treasures, but in engineering. How did builders working during the Mauryan and post-Mauryan periods create monuments capable of surviving more than 20 centuries of monsoon rains, temperature fluctuations, biological erosion, and human activity? Even more puzzling, how did they accomplish this without modern surveying equipment, structural analysis, cement, steel reinforcement, or written engineering manuals? The modern rediscovery of Dir Kathar occurred relatively recently. Archaeological surveys conducted in the late 20th century revealed an extensive Buddhist complex spread across a remote region of central India. Excavations uncovered stupas, monastic remains, stone railings, inscriptions, and fragments of pillars associated with the era of Emperor Ashoka. What initially appeared to be an isolated religious center soon emerged as one of the most important archaeological windows into the early expansion of Buddhism across the Indian subcontinent. Yet every excavation seemed to raise more questions than answers. One of the first mysteries involves the remarkable level of planning visible across the landscape. The stupas were not randomly scattered. Their placement suggests deliberate spatial organization that integrated terrain, visibility, movement, and ceremonial function. Modern survey measurements indicate that several structures occupy positions that maximize sightlines across the surrounding hills. Such planning may sound simple today, but achieving it over uneven terrain without modern instruments required sophisticated practical knowledge. Ancient builders had to measure distances, establish alignments, maintain proportional relationships, and account for natural topography. Similar planning principles can be observed at Sanchi, nearly 200 kilometers away, yet the exact methods used by ancient surveyors remain largely unknown. The stone components discovered at the site introduce another layer of mystery. Archaeologists identified fragments believed to be associated with Ashokan pillars. These pillars belong to one of the most technically impressive stoneworking traditions of the ancient world. Some surviving Ashokan pillars elsewhere in India stand more than 12 meters tall and weigh between 30 and 50 tons. Their surfaces display the famous Mauryan polish, a finish so smooth that it reflects light almost like modern polished stone. Researchers have attempted to reproduce this finish experimentally using traditional abrasives, yet no consensus exists regarding the precise combination of materials and techniques that created such extraordinary results. Under microscopic examination, some Mauryan surfaces exhibit a consistency that continues to challenge explanations based solely on simple hand polishing. Transportation presents an equally difficult puzzle. Large stone elements associated with Mauryan construction were often quarried dozens or even hundreds of kilometers from their final destinations. Moving a 40-ton monolithic pillar without steel cranes, modern roads, hydraulic systems, or mechanized transport would have required logistical capabilities on an enormous scale. Historians propose combinations of wooden rollers, sledges, labor teams, and river transport, but direct archaeological evidence remains scarce. Every surviving pillar raises the same question: how did ancient engineers repeatedly transport and erect structures weighing as much as modern military vehicles while maintaining such precision? Yet the greatest mystery of Dur Cathar may be found within the stupas themselves. Most ancient structures constructed primarily from earth and brick have long since vanished. Wind, rain, vegetation, earthquakes, and human activity gradually destroy even substantial monuments. Dur Cathar presents a different story. Despite more than 2,000 years of exposure, significant portions of multiple stupas remain recognizable today. This survival becomes even more remarkable when compared with the environmental conditions of central India. The region experiences annual monsoon cycles, capable of delivering substantial seasonal rainfall. Water is among the most destructive forces affecting archaeological structures. Once moisture penetrates a monument, repeated expansion, contraction, biological growth, and erosion can rapidly weaken the entire system. Modern conservation projects often struggle to protect masonry structures that are only a few centuries old. Yet Dur Cathar's builders created monuments that resisted environmental degradation for over 20 centuries. Archaeological studies suggest that this longevity was not accidental. Examination of surviving structures indicates the use of layered construction techniques. Rather than relying on a single material, builders combined compacted earth, stone fragments, brick components, and exterior protective layers into integrated systems. Modern engineers would describe such an approach as a composite structure. Each layer performs a different function. Dense inner cores provide stability. Intermediate materials absorb stresses. Exterior surfaces reduce weathering. Together they create a monument more resilient than any single material could achieve independently. What makes this particularly intriguing is that similar principles appear in modern geotechnical engineering. Contemporary embankments, dams, and earth-retaining structures often employ multiple layers designed to distribute stress and manage water infiltration. The builders of Dur Cathar appear to have reached comparable solutions through empirical observation more than 2 millennia earlier. The challenge is that no surviving manuals explain how they developed this knowledge. The mystery deepens when researchers analyze structural geometry. Stupas typically feature hemispherical or dome-like forms. Modern structural analysis demonstrates that curved geometries distribute loads efficiently by directing forces downward and outward. This reduces stress concentrations that might otherwise cause cracking or collapse. The same principle explains why arches and domes became fundamental elements of Roman engineering centuries later. Yet many early Indian stupas predate some of the most famous Roman examples. Were ancient builders consciously applying structural principles, or did generations of experimentation gradually refine designs toward optimal forms? The evidence remains inconclusive. Water management may hold another key to the extraordinary lifespan of the monuments. Even small failures in drainage can dramatically shorten the life expectancy of earthen structures. Surveys around Deur-Kothar suggest that builders paid careful attention to terrain gradients and runoff patterns. Many stupas occupy slightly elevated positions where water naturally drains away from foundations. This seemingly simple decision may have increased structural longevity by centuries. Modern archaeological mapping increasingly reveals that ancient builders possessed a sophisticated understanding of hydrology despite lacking formal scientific terminology. Another unresolved question is maintenance. Ancient communities likely repaired damage and reinforced weak areas over time, but the exact methods used at Deur-Kothar remain unknown. The site's survival may be due to both long-term care and exceptionally durable original construction, making it difficult for archaeologists to determine which factor mattered most. What do you think explains the extraordinary survival of the Deur-Kothar stupas for more than 2,000 years? Was it advanced engineering knowledge, centuries of maintenance, or a combination of both? Share your thoughts in the comments below. Buried within the dense forests of Campeche in southern Mexico, Hochob Archaeological Zone remained concealed beneath vegetation for centuries before modern archaeological surveys began documenting the site in the 20th century. The name Hochob roughly translates to place of the ears of corn, yet the city became known for something far more mysterious. Massive stone temples decorated with giant monster-like facades, unlike almost anything else in the Maya world. Unlike famous Maya centers such as Chichen Itza or Tikal, Hochob was built inside remote tropical terrain with no major rivers nearby and no obvious transportation network capable of supporting large-scale construction. Yet archaeologists discovered multi-room palace structures, ceremonial buildings, vaulted corridors, and enormous decorative facades constructed with astonishing precision. The deeper researchers investigated the site, the more Hochob began to look less like a forgotten jungle ruin and more like a technological puzzle left behind by the ancient Maya. The most iconic structures at Hochob are the enormous zoomorphic temple entrances, gigantic stone masks representing supernatural beings whose mouths form the doorway into the temple itself. These facades are composed of hundreds of carefully shaped limestone blocks fitted together with remarkable accuracy. What makes this mysterious is the level of precision achieved without iron tools, steel blades, cranes, or modern measuring equipment. Some joints between stones are so tight that even thin blades struggle to slide between them. Engineers comparing the stonework to later medieval masonry have noted similarities in precision, despite the Maya lacking metal-cutting technology available in Europe centuries later. The limestone used at Hochob is softer than granite, but that alone does not explain the consistency of the cuts. Researchers examining the surfaces discovered evidence of repeated abrasion polishing and controlled shaping techniques that would have required enormous labor coordination. Even more puzzling, Many decorative sections appear geometrically symmetrical across large surfaces, implying the builders possessed advanced planning systems and standardized measurement methods. Several archaeologists have suggested the Maya may have used chord-based geometric grids or proportional systems similar to those later documented in other ancient civilizations. Yet no surviving written technical manuals from the Maya world explain how such massive symbolic facades were designed and assembled so accurately in dense jungle conditions. One of the strangest engineering mysteries at Hotchob involves its surviving stucco surfaces. Tropical environments are among the worst possible places for exposed limestone architecture. High humidity, seasonal rainfall, heat, biological growth, and expanding tree roots rapidly destroy exposed structures. In many tropical regions, unprotected stone can degrade severely within centuries. Yet parts of Hotchob's stucco decoration have survived for over 1,000 years. Scientific analysis of Maya lime plaster from sites across the Yucatan Peninsula revealed evidence of sophisticated material processing. To produce lime plaster, the Maya heated limestone to temperatures approaching 800–900 degrees Celsius before mixing it with water and additives. Maintaining such temperatures consistently would have required highly organized fuel systems and advanced control of combustion environments. Researchers studying Maya plasters discovered traces of organic compounds, plant extracts, and mineral particles that may have improved water resistance and structural durability. Some modern materials scientists compare these mixtures to experimental self-healing lime mortars, where microscopic chemical reactions allow small cracks to reseal over time through calcite recrystallization. At Hotchob, the survival of detailed carvings despite centuries of tropical storms suggests the builders understood environmental engineering at a surprisingly advanced level. Some walls appear capable of shedding water efficiently due to subtle surface angles invisible at first glance. Others show evidence of layered finishing techniques designed to reduce moisture penetration. The mystery becomes even greater when compared to many later colonial structures in tropical America that deteriorated far more rapidly despite access to metal tools and later construction methods. Modern engineers consider tropical limestone terrain extremely difficult for long-term heavy construction. The porous bedrock absorbs water, fractures easily, and shifts over time. Yet Hotchob's buildings remained standing through centuries of storms, erosion, and environmental pressure. Archaeological surveys suggest the Maya may have constructed multi-layered foundations using compacted rubble, crushed limestone, and drainage materials to distribute weight across unstable ground. This resembles principles used in modern geotechnical engineering. What astonishes researchers is the scale of the achievement. Some structures at Hotchob weigh thousands of tons collectively, yet they show surprisingly limited subsidence compared to expectations for tropical terrain. Without reinforced concrete, steel frames, hydraulic excavation equipment, or modern soil analysis, the Maya somehow created stable ceremonial complexes capable of surviving for centuries. Comparisons are often made to other ancient civilizations that mastered difficult terrain, such as the Inca foundations at Machu Picchu or Roman harbor engineering along the Mediterranean. But unlike the Romans, the Maya worked without limb pozzolana concrete capable of hardening underwater. Unlike the Inca, Hotchob existed in humid jungle conditions that accelerate structural decay dramatically. This raises a disturbing possibility. The Maya may have possessed generations of accumulated empirical engineering knowledge far beyond what survives in the archaeological record. Hotchob also contains large corbel vaulted chambers, a hallmark of Maya architecture. Unlike true arches, corbel vaults are formed by stacking stones progressively inward until they nearly meet at the top. Structurally, this method creates enormous lateral pressure and instability. At Hotchob, some vaulted corridors appear unusually wide relative to their supporting walls. Modern structural simulations suggest several chambers approached dangerous load thresholds if constructed purely through basic trial-and-error methods. And yet many of these corridors survived for centuries. This suggests Maya architects deeply understood weight distribution, compression forces, and structural balance even without formal mathematical physics. Some researchers believe Maya builders refined their techniques over generations through repeated experimentation across cities in the Pus and Chens regions. The precision becomes especially mysterious considering the environmental conditions. High humidity weakens mortar, biological growth damages joints, and seasonal thermal expansion stresses stone structures continuously. Even so, parts of Hochob's vaulted architecture remain intact long after many younger historical buildings collapsed elsewhere in the world. Several structures at Hochob appear aligned with solar events, especially equinox and solstice positions. This is not unique among Maya cities, but the consistency of the orientations has generated debate among archaeologists. The Maya possessed one of the most advanced astronomical traditions in the ancient world. They accurately tracked Venus cycles, solar years, eclipses, and complex calendar systems. However, the precision implied at sites like Hochob raises difficult questions. How did observers in dense jungle terrain achieve such consistent alignments without telescopes or precision optics? Some theories suggest the Maya established long-term observational stations using horizon markers and repeated generational measurements. Others argue they may have used architectural sightlines integrated into ceremonial spaces. Comparisons are often drawn to solar alignments at Stonehenge or the astronomical planning of ancient Egyptian temples near Karnak. Yet Hochob's alignments were achieved in a tropical environment where vegetation growth constantly obstructed long-distance visibility. This makes the consistency even more difficult to explain. Perhaps the greatest mystery surrounding Hochob archaeological zone is logistics. The city was built deep inside tropical jungle with no major rivers nearby, while the Maya did not use large draft animals or practical wheeled transport for massive construction projects. Yet thousands of tons of stone were still quarried, moved, and assembled into enormous structures. Simply transporting multi-ton limestone blocks through hot, humid jungle conditions would have required extremely complex labor coordination. Researchers estimate that major Maya cities demanded millions of labor hours to complete large construction projects. The real mystery is not only how the Maya built Hochob, but how they maintained such a precise logistical system in one of the harshest environments imaginable. Do you think the Maya truly possessed engineering knowledge far beyond what history tells us? Share your thoughts in the comments below. In present-day Chhattisgarh in central India lies Ratanpur, once the capital of the powerful Kalachuri dynasty. Today it is a quiet town surrounded by forests, lakes, and temple ruins. Archaeologists have known about the site for centuries, but systematic studies during the colonial period and later surveys by the Archaeological Survey of India revealed something far more intriguing than a forgotten medieval capital. Beneath the surviving temples, collapsed walls, reservoirs, and scattered stone blocks lies evidence of an engineering tradition whose full sophistication remains only partially understood. Historians can identify the rulers who governed Ratanpur. They can estimate construction dates and reconstruct political events. Yet many of the technologies that allowed builders to create and maintain this urban center for hundreds of years remain difficult to explain. The mystery is not who built Ratanpur. The mystery is how medieval engineers working without modern surveying instruments, reinforced concrete, steel machinery, or written engineering manuals achieved such remarkable results. The first clue appears in the city's overall layout. Ratanpur was not constructed randomly. Archaeological mapping reveals a carefully organized settlement centered around religious monuments, defensive structures, artificial water bodies, and transportation routes. The arrangement suggests advanced planning extending across several square kilometers. Such planning required accurate measurements, labor coordination, and long-term resource management. Similar organizational complexity is often associated with major centers such as Angkor in Cambodia or the Chola capitals of southern India. Yet Ranthambore remains far less studied despite displaying many of the same characteristics. Among the most impressive surviving structures is the Mahamaya Temple, one of the oldest and most significant monuments in the region. Built primarily from stone blocks, the temple demonstrates an extraordinary understanding of structural balance. Modern engineers examining ancient Indian temples frequently note that many survived earthquakes, monsoon cycles, and centuries of weathering despite lacking steel reinforcement. Ranthambore presents the same puzzle. The temple's weight is distributed through a system of load-bearing walls, interlocking stone components, and carefully calculated proportions. The builders possess no computer models, yet the structure has remained standing for nearly 1,000 years. Researchers can measure the geometry, but the precise methods used to calculate stability remain uncertain. The mystery deepens when examining the stone itself. Some of the blocks display carving precision measured in millimeters. Decorative patterns remain visible despite centuries of exposure to rain, humidity, biological growth, and temperature fluctuations. Geological studies suggest that builders deliberately selected stone varieties capable of resisting weathering. This implies practical material science knowledge developed through generations of experimentation. The challenge is that almost none of the technical knowledge survived in written form. The monuments remain, but the engineering principles behind material selection largely disappeared. Water management may represent the greatest technological achievement of ancient Ranthambore. Central India experiences dramatic seasonal variations. During monsoon months, rainfall can be intense. During dry periods, water becomes far more limited. Sustaining a large urban population under such conditions required sophisticated hydraulic engineering. Archaeologists have identified reservoirs, tanks, channels, and interconnected water storage systems throughout the region. Some reservoirs remain functional even today. What makes these systems remarkable is their apparent ability to regulate water flow naturally. Engineers had to calculate gradients carefully enough to move water efficiently while preventing erosion. A slope that is too steep accelerates destructive flow. A slope that is too shallow prevents circulation. Modern hydraulic engineers solve such problems using precise calculations and surveying equipment. Medieval builders at Ranthambore achieved similar outcomes using technologies that remain poorly documented. Comparisons with other hydraulic civilizations highlight the significance of this accomplishment. The Roman aqueducts transported water across hundreds of kilometers, with gradients often measured in centimeters per kilometer. Angkor's reservoirs transformed Cambodia's landscape through massive water control projects. The Hohokam culture in North America built hundreds of kilometers of irrigation canals. Ranthambore operated on a smaller scale, yet the same engineering principles appear evident. The unresolved question is how knowledge of terrain analysis and water behavior was transmitted across generations without surviving technical manuals. The transportation of construction materials introduces another mystery. Many stone blocks used in temples and fortifications weigh several tons. Moving such material requires substantial logistical planning. Even modern construction projects rely on cranes, vehicles, and specialized equipment. Medieval builders depended primarily on human labor, animals, ropes, ramps, and mechanical advantage. Historians can propose theoretical methods, but direct evidence remains limited. No detailed engineering records explain how the larger stones reach their final positions. Experimental archaeology offers clues. Reconstruction suggests that teams using wooden rollers, earthen ramps, and coordinated pulling systems can move surprisingly heavy loads. Similar methods have been demonstrated for Egyptian pyramids, Roman monuments, and Inca architecture. Yet each environment presents unique challenges. The terrain surrounding Ratanpur includes seasonal wetlands, uneven ground, and dense vegetation. Moving large stones across such landscapes would have required extraordinary organization. The exact techniques remain uncertain. The defensive architecture of Ratanpur presents another puzzle. Historical accounts describe the city as a major political center protected by fortifications. Portions of these defensive systems survive today. Archaeologists believe the city's designers integrated walls, gates, water bodies, and natural topography into a unified defense network. Such integration required strategic planning extending beyond individual buildings. Comparable military engineering can be observed at forts such as Daulatabad in Maharashtra or Chittorgarh in Rajasthan. Yet many details of Ratanpur's original defensive system have vanished, making reconstruction difficult. One particularly intriguing aspect is the relationship between hydraulic infrastructure and defense. Several reservoirs may have served dual functions. During peaceful periods, they provided water storage. During conflict, they potentially acted as obstacles slowing attackers. This combination of civil and military engineering demonstrates a level of systems thinking often underestimated in discussions of medieval technology. Astronomical alignment may also have played a role in the city's design. Many Indian temples incorporate orientations linked to solar events, cardinal directions, or ritual calendars. Preliminary studies suggest certain structures at Ratanpur follow deliberate alignments rather than random positioning. Similar patterns occur at Konark, Khajuraho, and numerous sacred sites throughout South Asia. Whether these alignments served symbolic, practical, or astronomical functions remains debated. What is clear is that achieving consistent orientations across multiple structures required reliable surveying methods. The greatest mystery of Ratanpur may be the invisible technological ecosystem that supported construction itself. Every monument implies the existence of quarry workers, surveyors, stonemasons, transport specialists, hydraulic engineers, architects, and administrators. These specialists required training systems capable of preserving technical knowledge over generations. Yet the workshops where that knowledge was taught have largely disappeared. The tools have vanished. The instruction methods are unknown. Only the finished products remain. Rising 575 meters above sea level on a massive limestone mountain overlooking the Isthmus of Corinth in southern Greece, the stronghold dominated one of the most strategically important corridors in the ancient Mediterranean. For more than 2,000 years, Greeks, Romans, Byzantines, Franks, Venetians, and Ottomans all occupied the same summit. Yet the greatest mystery of Acrocorinth is not its military history. It is the extraordinary engineering hidden inside the mountain itself. Beneath the walls lies evidence of ancient hydraulic systems, underground chambers, water management technology, and logistical capabilities that remain only partially understood. Modern archaeologists can map the fortress using drones, laser scanning, and digital terrain models. But many of the technical decisions made by its builders continue to puzzle researchers. Acrocorinth, known today as Acrocorinth, stands above the ancient city of Corinth in Greece. The fortress occupies the summit of a steep limestone outcrop covering roughly 3 square kilometers. Ancient authors, including Strabo and Pausanias, described the site, ensuring that its location was never truly lost. However, systematic archaeological investigation accelerated during the 19th and 20th centuries through Greek, American, and international excavations. These studies revealed that the visible walls represent only a fraction of the much older and more complex engineering landscape extending beneath the surface. The greatest engineering mystery at Acrocorint involves water. Throughout history, mountain fortresses shared one fundamental weakness: water supplies could be cut off during a siege. Many famous strongholds eventually surrendered not because their walls failed, but because their defenders ran out of water. Acrocorint appears to have solved this problem. Archaeologists identified multiple cisterns, reservoirs, wells, and underground access routes connected to natural springs. The most famous is the Upper Perrine Spring, a water source carved deep into the limestone beneath the summit. Reaching the spring required descending through rock-cut stairways extending into the mountain. The engineering challenge is enormous. Limestone mountains contain highly complex underground drainage systems. Modern hydrogeologists often rely on geological surveys, drilling programs, and computer models to identify underground water pathways. Ancient builders possessed none of these tools, yet somehow they located reliable water sources with remarkable precision. Comparisons with other fortified sites reveal how unusual this achievement was. At the fortress of Masada in Israel, engineers built gigantic cistern systems to capture seasonal floods. At Acrocorint, builders appear to have combined natural springs with artificial storage systems. This hybrid solution may have provided greater long-term reliability than many contemporary fortifications. Researchers still debate exactly how ancient engineers identified these underground water resources. Was the knowledge based on generations of geological observation? Did they recognize subtle surface indicators revealing hidden groundwater? The answer remains uncertain. Beneath the fortress lies another puzzle. Numerous tunnels, stairways, chambers, and rock-cut installations penetrate deep into the limestone. Some clearly served hydraulic purposes, while others remain difficult to explain. Several underground spaces occupy locations that offer little obvious military value. They're too isolated for routine storage and too inaccessible for large-scale habitation. Some researchers propose that parts of the system originated as sacred spaces associated with earlier religious activity. Others suggest emergency shelters, hidden supply routes, or components of an unfinished hydraulic network. The problem is that the fortress evolved continuously for over 2 millennia. Greek structures were modified by Romans, Roman structures were altered by Byzantine builders, and Byzantine installations were rebuilt by Crusaders, Venetians, and Ottomans. Each phase erased evidence from earlier phases. Laser mapping has revealed architectural inconsistencies, suggesting that some underground spaces may be significantly older than the visible fortress walls. Determining their original purpose remains one of the site's most difficult archaeological challenges. Every stone at Acrocorint presents a logistical question. The fortress walls stretch for approximately 2 kilometers around the summit. Certain defensive sectors contain massive blocks weighing several tons. All construction materials had to be transported up steep mountain slopes before being shaped and installed. Modern engineers calculate construction logistics using load capacities, transportation models, and mechanical equipment. Ancient builders relied primarily on human labor, animals, ropes, wooden sledges, and simple lifting devices. The scale becomes clearer when compared with other mountain fortifications. Transporting materials to Acrocorint would have been significantly more difficult than building walls on level terrain such as those surrounding many Greek cities. Similar logistical challenges occurred at sites like Mycenae, Pergamon, and Masada, yet Acrocorint's elevation made every stage of construction more demanding. Archaeologists still cannot fully reconstruct the transportation systems used during the earliest construction phases. No written manuals survive, and the engineering knowledge disappeared long ago. One of the most remarkable aspects of a Crocorant is that its defences seem to emerge directly from the mountain itself. Rather than forcing the landscape to conform to architecture, builders integrated architecture into the existing geology. Cliffs became walls, narrow ridges became controlled access points, and natural bottlenecks evolved into defensive choke points. Modern military analysts often describe defensive depth as one of the most effective principles of fortification. Acrocorant demonstrates this concept centuries before formal military engineering texts discussed it systematically. Attackers advancing toward the summit faced multiple defensive zones. Each gate forced movement into predictable directions. Elevated positions provided overlapping fields of observation. Defenders could concentrate force at critical locations while exploiting gravity itself as a weapon. Some historians compare the fortress to a gigantic natural war machine. The mystery is whether this sophistication emerged gradually through centuries of adaptation, or whether the earliest planners already understood the defensive potential of the mountain with surprising precision. Perhaps the most overlooked mystery concerns endurance. Historical records indicate that Acrocorant repeatedly survived prolonged military threats. To achieve this, the fortress required food storage, water management, sanitation systems, maintenance facilities, and organizational planning. Scientists studying ancient siege conditions estimate that an adult requires at least several liters of water daily under warm Mediterranean conditions. A garrison numbering even a few thousand individuals would therefore consume enormous quantities of water every month. The cisterns preserved at Acrocorant suggest large-scale planning, but researchers still debate the site's maximum sustainable population during wartime. This creates a fascinating engineering problem. How did ancient administrators calculate storage requirements? How much water could the reservoirs actually hold? How long could defenders survive complete isolation? Despite extensive research, no definitive answers exist. Ancient writers described a famous sanctuary dedicated to Aphrodite occupying the summit of Acrocorant. The temple was among the most celebrated religious sites in ancient Greece, yet surprisingly little survives. Archaeologists recovered fragments, foundations, and scattered architectural remains, but the complete structure remains largely unknown. This absence creates a significant historical mystery. How could one of the most famous sanctuaries in the Greek world disappear so completely? Repeated rebuilding offers part of the explanation. Religious structures were transformed into churches, later converted into mosques, and repeatedly altered during successive occupations. Valuable stone blocks were reused in newer buildings, and earthquakes may have accelerated destruction. Nevertheless, researchers still cannot confidently reconstruct the temple's exact dimensions, architectural appearance, or engineering details. One of antiquity's most famous monuments survives primarily through texts rather than stone.